Good morning, everybody. Can you listen to me? Please raise your hand. Everybody, still strength yet to come. Today will be the big day, sir. Very big day to conclude everything. And I told Nasser after 10 days or 1 week or 10 days, I will put a doubt session also, which I will plan. But schedules are very tight. That is what yesterday's schedule manager told. But we will do something. Because the main target now, it is already November 5th now. So the target should be to complete the syllabus as early as possible. Okay, our main target is to really complete the syllabus. Yes, everybody, are you ready now? Shall I start? Still, why so much strength? I know yesterday Diwali, etc., but strength is very, very low. Strength is really low. Quick review what we did yesterday. I want to quickly review what we did because yesterday was a big day. We started with first order and completed a lot and gave the formulas for second order. Okay. Yes, this is where we started yesterday. Yes, this is where we started, everyone. Yes, everyone, please listen what we did yesterday. See, we started after the definitions of transients. We started with first category. that is source free first order. Source free means it is turn off process, and first order is only one energy storage element in that RC circuit. And in RC circuit, the state variable is voltage across capacitor. Okay. And then we got the expression from mathematics that this capacitor is discharging exponentially based on its time constant. If time constant is more, slowly it will decay. But if time constant is small, quickly it will decay. Then after getting that, yes, I got the expression. Okay, I gave the definition of what is called time constant, all the other possible parameters, and then RL circuit, state variable is current through inductor. And again, this also will decay exponentially based on the time constant. Here, time constant is L by R. So the stored magnetic energy in the inductor will be released through the resistor in exponential form. Then again, all the parameters we got. So in category 1, simple 4 formulas. If it is a RC circuit, voltage across capacitor state variable V0 e power minus T by tau, and tau is RC. If it is an RL circuit, state variable is current through inductor, I0 e power minus T by tau, and tau is L by R. Then units of time constant is seconds, and we got some problems here. How to find time constant of simple first order circuits. Okay, simple first order circuit. Yes, but here you see this is second order and the two non-standard circuits. Yesterday I gave the approximate formulas for second order series RLC and parallel RLC, but this is not coming into that category also. See here, this double inductor is neither pure series RLC nor pure parallel RLC. So here really there is no single time constant. Okay, everybody please understand. Here, yes, here there is a double inductor. Here there is a double inductor. When there is a double inductor, there is no single time constant. Okay. Either you have to solve simultaneous differential equations or go to Laplace. But yesterday, what formulas I gave is only valid for standard series RLC and standard parallel RLC, approximate time constant formulas. Okay. Then after that, yes, we started category 1 problems. All these category 1 problems, RL circuit, RC circuit. Okay. Then, yes, dependent source problem. Okay. Then we did this problem, which everyone thought it is second order, but it is two independent first orders. Okay. Because L and C are not interacting. Then this is a recent GATE 2018 bit. Okay. Like we did. Then we came to category 2. Category 2 is step response of first order. That is turning on process. Again, RC circuit state variable is voltage across capacitor. This formula you have to remember. V of infinity plus V of 0 minus V of infinity power minus T by 2. Okay. Then stay with initial condition, without initial condition. Then we got power, energy, okay, and remaining parameters and efficiency. Then RL circuit also, yes, state variable is inductor current. You have to remember this formula, I of infinity plus I of 0 minus I of infinity for minus t by tau. Again, here current is a state variable. Okay, all the parameters and efficiency of RL circuit is 0. Now we did some problems on first order step response problems. Okay, and bulb problems, some applications. Okay, very interesting problems we did here also. We did magnetic circuit problem and we did even dependent source model. All models I'm covering, sir. Then we came to the formulas of second order, source free second order, but standard series RLC. Here state variable I took casually, current through inductor, series nasser, current I took which is equal in all the elements. Then here three types of responses can exist based on the values of RLC. So alpha is called damping factor and omega naught is called undamped natural frequency. See, damping ratio zeta is a different concept, please. Then based on that, yes, based on that, I got the complete, yes, details. And parallel RLC also, I took casually the, yeah, voltage across capacitor state variable because in a parallel system, voltage is same. Again, based on the types of, based on the values of RLC, here three types of inputs: overdamped, critically damped, and underdamped. Okay. And I did just some numericals based on the formulas to understand the meaning of these formulas. Then here time constant concept I was telling. Yeah, time constant concept. So this time constant concept is applicable only for standard series RLC and standard parallel RLC. Okay, na? Then in that regard, then we started even category 4 only formulas. That is step response of second order series RLC. Okay. Yes, in series RLC here dominant state variable is voltage. Now here it is important to select state variable. Why? Because here, if you take current through inductor as state variable, current becomes 0 as t tends to infinity. Yes or no? Here, current becomes 0 as t tends to infinity. That is important. Yes, here current becomes 0 as t tends to infinity. That is very, very important to observe. Okay. Current becomes 0 as t tends to infinity. That is why voltage across capacitor is very, very important for us. Okay. That is why the dominant state variable is voltage across capacitor. And again, here, because it is turn on process, there is step response. That is steady state and transient state. Steady state here we know directly DC steady state, but transient state again depends upon the values of RLC, either overdamped, critically damped, or underdamped. This is how the response look. Then in parallel RLC, yes, I took current as excitation. Here switch opening will excite this network. Okay. Here switch closing will excite the network. Here switch opening dual. Easy to explain, sir. Don't worry. Whatever it is, we can take. But here again, I took dominant state variable as current because voltage across capacitor does not exist as t tends to infinity. As voltage across capacitor does not exist, only current through inductor exists. Yes, we took the dominant state variable as current through inductor. And again, here total response is forced plus natural. Steady state we got, but natural, again, depending upon the values of RLC, there are three types of responses. Okay, either overdamped, critically damped, underdamped. And that is how the response look. So now, sir, now we are coming to big conclusion. So now I'm writing, see here in determining the complete solution to second order circuits. Now everyone please pay attention. Now in determining the complete solution to second order circuits, now this steady state part we can do. Okay, now steady state part we know DC steady state, DC input, AC steady state, AC, because steady state analysis we already did. Then S1, S2 also we know the formulas. Minus alpha plus or minus root of alpha square minus omega naught square. Now alpha value also we know. For series RLC, it is R by 12. And for parallel RLC, 1 by 2 RC. And omega D value also we know. That is damped frequency, root of omega naught square minus alpha square. So what is the big challenge here? The big challenge is to find this constants A1, A2. Everyone should understand this, sir. The biggest challenge here is to find constants A1, A2. Now in second order, there are 2 constants. Third order, 3 constants. Fourth order, 4 constants. In first order, it was so casual. Yes, sir. In first order, it was so casual that we just went to initial conditions, previous state we got. But here in second order, it is not possible, sir. 2 constants. So we require at least 2 equations. So initial conditions we are starting now. So category 3, category 4, I only gave formulas. Everyone listen now. Category 3, category 4, I only gave formulas. But to do the complete solution, I need at least 2 equations to solve the constants A1, A2. Hence, initial conditions are important. Chalo, now initial conditions. So now I'm writing a very, very important note. Yes, continuing from here, everybody. Yes, I'm continuing from here. Everybody should listen now. So what I want to say is, yes, everybody, what I want to say that in determining, okay. Yes, now I'm writing a note. In determining the complete solution to these second order circuits. Yes, to determine, in determining the complete solution to these second order circuits, here it is a big challenge. It is a big challenge to find the correct values, correct values of constants A1 and A2 in determining the complete solution to these second order circuits. Here it is a big challenge to find the correct values of constants A1, A2. Hence, yes, sir. Hence, we need to determine. Initial conditions. Yes. Hence, we need to determine initial conditions. Chalo, sir. So, after writing the formulas of category 3, that is source free second order, and category 4, step response second order, now we are saying that it is a very big challenge to find the correct values of constants A1, A2. Hence, we need to determine what initial conditions. So now we are going to category 5. That does not mean that category 3, category 4 are over. No, sir. Category 3, category 4, only mathematical understanding is over. But to get the solution, I need initial conditions. So first we are learning initial conditions. So now I am writing category 5. Category 5 is initial condition problems. Initial condition problems. I also call this as problems at t equal to 0 plus. Okay, problems at t equal to 0 plus. This is only state solution, or yes, transient state problems. Transient state problems, but not transient solutions. Okay, please understand. I give 3 names to it. First of all, initial condition problems are called problems at t equal to 0 plus, or I say transient state problems. Yes, initial condition problems are problems at t equal to 0 plus, that is transient state problems or transient state problems. Okay, now please understand, this is called transient state problems. Okay, now so initial condition problems are problems at t equal to 0 plus. That is also called transient state problems. Okay, now chalo, now sir, to understand this, first I am writing equivalent circuit representation of passive elements in transient state, that is at t equal to 0 plus. Okay, equivalent circuit representation of passive elements in transient state. Chalo, first element, yes, element and representation, yes, representation. I will write directly, otherwise circuit at t equal to 0 plus, element and circuit at t equal to 0 plus. Okay, na? Chalo, first pure resistor. Now resistor is independent to frequency, so it is also same. Now pure inductor at 0 plus. Now see, sir, this basics we already got here. Everybody listen now. See, this basics we got already in the introduction. You see here, introduction we got already. This table you see, sir. Yes, 0 plus. Everybody see this third column. So inductor at 0 plus is like open circuit. Yes or no? That is important here. Inductor at 0 plus is like open circuit. Yes or no? Yes, open circuit. This acts like open circuit. That is very, very important. Now, extra thing I am teaching. Inductor, okay, with initial condition. Inductor with initial condition. So first of all, 2 things. Inductor acts like open circuit. At the same time, inductor will not allow sudden change in current. So it should allow the same current to flow. Yes, it should allow the same current to flow. Yes, in the same direction. So this is the representation of inductor with initial condition. So first of all, inductor acts like open circuit. At the same time, it should allow the current to flow. Yes. So I'm showing that current in parallel to open circuit. Then capacitor alone. Okay, capacitor alone. Now again, sir, we know the basics. Yes, we know the basics. If you observe, yes, if you observe, Capacitor at 0 plus short circuit. See, sir, short circuit. Capacitor at 0 plus is like short circuit. Everyone should understand. Is acting like short circuit. Short circuit. But capacitor with initial voltage. Okay. Now capacitor with initial voltage. Initial voltage and capacitor. First of all, capacitor acts like short circuit. Yes, capacitor acts like short circuit. At the same time, capacitor will not allow sudden change in voltage across it. So we should represent the same voltage, yes, of polarity and magnitude in series, because you cannot show voltage source across short circuit, and you can never show current source in series to open circuit. Both are violation of KVL and KCL respectively. So these are the 5 things that you have to remember, sir. Yes, first resistor, independent of frequency, same. Inductor without initial condition, open circuit. Inductor with initial condition, open circuit, and current also should be maintained because inductor will not allow sudden change in current. The current also you should show. Then capacitor without initial condition, short circuit. Now capacitor with initial condition. Okay, this came from our basics, what we discussed so far. Okay, now with these things, chalo, now we are coming to very important question. Chalo, first simple question. Find, everyone watch this question, sir. I of 0 plus, yes, di of 0 plus by dt. D square I of 0 plus by dt square. So here I am asking a question. Find I of 0 plus di of 0 plus by dt and d square I of 0 plus by dt square. Okay, now in that regard, this is the question I'm giving. Everybody should watch this question. Very simple problem to start with. Okay, chalo, imagine everybody, chalo. Yes, everybody. So the switch is closing at t equal to 0, and I'm asking what is I of 0 plus di of 0 plus d square I of 0 plus by dt. Now, whenever you see 0 plus, now please understand, sir. Whenever you see 0 plus in the circuit, yes, is 0 plus in the question. Now these are different problems. Okay, whenever you say 0 plus in the circuit, these are different problems because these are called transient state problems, but here solution is not important. Okay, so whenever you see 0 plus in the circuit, these are different problems called transient state problems. Here solution is not asked. Now see, here luckily this is a very simple series RL circuit. Listen carefully, sir. Here it is a very simple series RL. So whenever you get simple series circuits, parallel circuits, you need not use this and waste your time. You can still do the same way. Yes, you can still use this. But what is my suggestion is, if they are simple circuits like in Genco, Transco, IES bits, which are simple series circuits or simple parallel circuits, you need not take this equivalent circuit and waste your time. My suggestion is directly write differential equation. Now see, now whenever you see 0 plus problems, here solution is not important. State, like what is the meaning? What is the current at immediately after switching? I of 0 plus means what is the current just after transient, or at the instant when transient occurred, what is the sudden current? Then what is the initial rate of change in current? What is the initial rate of change in current? That is very important parameters, sir, for designers. What is initial rate? That rate is very high, then you have to put a snubber. Okay, filters. What is the acceleration? Current acceleration. Okay, so the meaning of this is I of 0 plus di of 0 plus d square I of 0 plus by dt square. Now, whenever such problem is asked, always start from 0 minus. Always start from, yes, t equal to 0 minus. At t equal to 0 minus, switch was open or close? Switch was open. Yes, at t equal to 0 minus, switch was open. Okay, at t equal to 0 minus, switch was open. Please understand this. At t equal to 0 minus, switch was open. When switch was open, I of 0 minus is 0, which is also equal to I of 0 plus, which is also equal to I of 0 plus, because inductor will not allow sudden change in current. Okay, what is the reason? What is the reason? Yes, the reason is inductor will not allow, okay, sudden change in current. Sudden change in current. Okay, so always remember I of 0 minus, switch was open, current is 0. So that is also equal to I of 0 plus, because in series there is inductor. Inductor will not allow sudden changing. So first answer we got 0. First answer we got 0. Then now what I want, I need di of 0 plus. So directly I'm writing KVL. I told sir, if it is inductor problem, KVL. Directly if I write KVL, minus 100, yeah, plus 5i plus 1 milli di by dt equal to 0. Okay, minus 100 plus IR plus LDI by dt. Now I'll modify this formula at t equal to 0 plus. If I mod this at 0 plus, minus 100 plus 5i of 0 plus 1 milli di of 0 plus by dt equal to 0. Okay. So now what is I of 0 plus? I of 0 plus is 0. I of 0 plus is 0. Okay. Na? So now directly this di of, because I of 0 plus we got 0 na. So this di of 0 plus by dt will be, take this 100 that side, plus 100 by 1 milli. So this is 100 kilo ampere per second. 100 kilo ampere per second. 100 kilo ampere per second. Okay, that is the next thing. Okay, 100 kilo ampere per second. So that is the second answer. So if this current rate of change is very high, then you have to put a filter, etc. Okay, otherwise it is okay. Okay, so now what is d square I want? Now differentiate again. This you differentiate again. So I will write here. Differentiate the equation. Okay, differentiate again. Okay, differentiate again. What you will get? So if I differentiate this equation again, this is a standard equation, sir. Standard equation. Now if you differentiate this again, okay, this I modified by 0 for 0 plus, I got this answer. But if I differentiate again, differentiation of constant is 0. So this become now 5 di by dt. Okay, and here 1 milli d square I. Yes, 1 milli d square I by dt square equal to 0. Now again I will modify for t equal to 0 plus. So this becomes 5 di of 0 plus by dt plus 1 milli d square I of 0 plus by dt square equal to 0. So now this is already got what we got here, this 100 kilo ampere per second. This is already 100 kilo ampere per second. So if you substitute, now we are getting the answer that this d square I of 0 plus by dt square is equal to yes, this becomes how much? Minus, see, this is 500k into 5 minus 500k by 1 milli. Don't forget this 1 milli. So this is minus 500 kilo by milli mega ampere per second square. Okay, mega. So these are the three answers, sir. See, first answer, yes, and that is I of 0 plus is 0. Okay. Second answer, di of 0 plus by dt is 100 kilo ampere per second. And the third answer, d square I of 0 plus by dt square is minus 500 ampere per second. Okay. So from this you can tell. So the current just after the change is 0. That is okay. But the rate at which it is changing is disaster. That is very dangerous. So it is changing at the rate of 100 kilo ampere per second. Like in thyristor, we study di by dt rating, sir, like that. If that is not good or sufficient, if it is sufficiently large, which may damage thyristor, then here instead of the switch, imagine thyristor. So instead of this normal switch, imagine thyristor, then the thyristor may burn. So what you have to do, you have to put an extra snubber inductor, extra, because inductor will not allow sudden change in current, like that. So all our houses have this snubbers, sir. Our adapter has large inductor, our television has large inductor in it. Okay, our AC regulator of our air conditioner. So they protect these things. Okay, now that is the meaning. That is the real meaning here. Okay, then d square I by dt square, yes, minus 500 mega ampere per second. Okay, that is all the thing. Yes, you should understand. So now I am coming to a very important problem here. Okay, now I am asking find. This is the second model. I of 0 plus, V of 0 plus, di of 0 plus by dt, dv of 0 plus by dt, then I of infinity and V of infinity. Okay, very interesting question, sir. Okay, I'm asking this question to find these things. And it's a very practical circuit here. This is 200 volt, 2 ohm, 1 millihenry, 10 microfarad, 6 ohm, 3 ohm, 2 ohm. Okay, 6 ohm, 3 ohm and 2 ohm. And the change is this 6 ohms is coming at equal to 0. So there is an extra load. There is an extra resistance is turning on the circuit, extra heater. Like imagine that in your house, like already in your house, there is a sufficient load. Okay, you're already running television, light, fan, etc. Now you are adding an extra heater. Heater is like resistor, na? There is a meaning. Now he is asking this current through inductor parameters and voltage across capacitor parameters. So please understand this question. Everybody read this question. Previous problem was very simple series RL. Okay, previous problem was a very simple series RL. Okay, nothing was there. So happily I wrote the differential equation we got. But this is something different. Everybody should understand this. Okay, everybody please understand this. See here, find I of 0 plus V of 0 plus. What is the meaning of I of 0 plus? I of 0 plus means, yes, current through inductor just at the instant when we turn on. V of 0 plus is also current through, voltage across capacitor immediately when you turn on. Di of 0 plus by dt. Yes, what is the meaning of di of 0 plus by dt? The rate of rise or change in inductor current. dv of 0 plus by dt, the rate at which the voltage across capacitor is changing. And I of infinity and V of infinity. I of infinity means final value of current through inductor, and V of infinity is final value of voltage across capacitor. Okay, now that is what we are trying actually. Okay, sure. Now listen, sir. Now here again, these are initial condition problems. These first 4 bits at least are initial. Here d square and dv square I am not using. Later we will do even such problems. But here my initial challenge is to find, yes, my initial challenge is to find these 2 things. Okay, now, yes, my initial challenge is to find these 2 things. Okay, now. Now, I told you, sir, whenever such questions are asked, first start from t equal to 0. That is my, yes, first solution. Yes, part 1. Okay, I am writing part 1 solution, which is previous steady state, past steady state, which is t equal to 0 minus. Chalo, when I go to t equal to 0 minus, yes, everybody please understand, at t equal to 0 minus, you know, what happening the previous DC steady state. Yes, in previous DC steady state, you know, inductor short, this resistor did not come, and capacitor is open. Okay, this is the previous steady state. Okay, so this is clearly 200 volt, 2 ohm. This is also 2 ohm, and this is 3 ohm. Because this resistor did not come, inductor short, capacitor open. Now I am finding these 2 things. Yes, what is that I am finding? One is I of 0 minus, and one is V of 0 minus. Okay, here voltage cannot exist. So now clearly this I of 0 minus is how much? 200 by 5, which is 40 amperes, which is also equal to I of 0 plus. Why? Because, yes, why? Because, yes, inductor will not allow sudden change in current through it. So first bit we got. Similarly, if I go to V of 0 minus, V of 0 minus is the voltage across this resistor. If I do voltage division rule, that is total voltage into, this is same, okay, same by sum is 5. So this is 40 into 3, 120 volt. That is also equal to V of 0 plus. Why? Because capacitor will not allow sudden change in voltage. Capacitor will not allow sudden change in voltage. Okay, na? Capacitor will not allow sudden change in voltage. That is the reason. Okay, na? Capacitor will not allow sudden change in voltage. Please understand this. Okay, capacitor will not allow sudden change in voltage. Okay, yes, everybody please understand. Okay, yes. In the past steady state, we got 2 answers. So I of 0 plus is I of 0 minus because inductor will not allow sudden change in current. V of 0 minus is V of 0 plus because capacitor will not allow sudden change in voltage. That is coming from the previous steady state. Now I want di of 0 plus by dt and dv of 0 plus by dt. See, in the previous problem, how I got this di of 0 plus by dt? By simply writing a KVL if it is an RL circuit in series, or if it is an RC circuit, write a KCL. But no, sir, here we cannot do, because this is neither pure series nor pure parallel. You remember I call this as non-canonical, which I told you while phasor diagram. So I call this as non-canonical, non-standard because, yes, I call this as non-canonical, non-standard because this is neither pure series where current is equal in all the elements nor pure parallel. So in such case, you cannot write a simple differential equation like this. So what we have to do, here we need to build the 0 plus circuit. This is very important table, sir. Now let me build the 0 plus table. Chalo, I'm going to part 2. Yes, this part 2 solution, yes, is the, yes, present transient state. Present transient state. Okay, that is T equal to 0 plus state. Now I am writing the equivalent circuit representation at 0 plus. So first of all, what is the change that happened? This extra 6 ohms came. So the change that happened is, everybody watch this please. The change that happened is extra 6 ohm came. Due to which what happened now? This is resistor. Okay, this is already 200 volt and this is 2 ohm resistor. Now the change is that switch has closed, extra 6 ohms came. But what happens to inductor? Inductor with initial condition, how it will be? Inductor with initial condition is open circuit and current also should be there. So already we know the initial current through inductor is how much? 40 ampere. So inductor open, yes, with initial current. That initial current is 40 amperes. This is very important. So 40 amperes. This is the inductor with initial condition. Then the change, what is the change here? The change is that extra 6 ohms came. Okay, extra 6 ohms came. What about capacitor? Capacitor with initial condition is short and voltage. Yes, capacitor with initial condition should be short. So this is already there. Now it is short plus initial voltage. But what is the initial voltage of capacitor? 120 volt. This is 120 volt. 120 volt. And this resistor is still there. This resistor is still there. Okay, so please understand, sir. This is a 0 plus circuit. First time we are writing in circuit theory. So based on the fundamentals what we discussed, okay, because in this problem it is neither pure series nor, if it was pure series or pure parallel, I would have write differential equations, sir, but it is not possible here. That is why for the first time we are writing the 0 plus circuit. Now 0 plus circuit, the basics I gave here. Chalo, based on that I wrote inductor with initial condition, open circuit, and current should be in the same direction and same magnitude. Same direction and same magnitude. Then capacitor, short circuit with initial voltage. It should be in the same polarity. It should be in the same polarity what it is coming. Okay, chalo, we got this. Now here our challenge is to find what, sir? Our challenge is to first find, okay, we need to find what are the things. One is di of 0 plus by dt. Yes, we need to find this. And dv of 0 plus by dt. So now we need to find this. But I will use Ohm's law. What is that Ohm's law? That is nothing but VL of 0 plus by L. Because V is LDI by dt, I will get like this. Okay. Then here also IC of 0 plus by C. Okay. IC of 0 plus by C. Okay. That is how I will get. Okay, one is VL of 0 plus by L and one is IC of 0 plus by C. Okay, that is how I will get. Everybody please understand what I'm trying to do. Yes, I will get like this. Okay, one is VL of 0 plus by L and one is IC of 0 plus by C. Okay, one is VL of 0 plus by L and one is IC of 0 plus by C. That is how I will get. So to get that rate of change in inductor current and rate of change in capacitor voltage, yes, to get that rate of change in inductor current and rate of change in capacitor voltage, okay, yes, I need VL of 0 plus by L and IC of 0 plus by C. Now these are called ulta state variables. See, what are the correct state variables? We know capacitor voltage and inductor current, na, sir. Actually, current through inductor and voltage across capacitors are state variable. But to find the rate at which current through inductor and voltage across capacitor is changing, I need to find the ulta to the state variables. Now, inductor voltage at 0 plus and capacitor current at 0 plus are called ulta state variables. Chalo. Now I need these two, sir. See, from the circuit, I'm getting them. Everybody watch this, please. So I'm using passive notation. What is that? See here, current is entering in inductor. So this will be VL of 0 plus. And capacitor is charging like this. This should be IC of 0 plus. So these are called ulta state variables. Now, if you can find these two, yes, if you can find these two, I can substitute here and substitute here and take the LNC value to get this. Very, very interesting, na, sir. Previous problem is just a simple KVL I wrote, but here it is not possible. Chalo, now, sir, listen. So in 0 plus circuit, you should find the ulta to the state variables, like that you remember. Now, this is not easy circuit. Now I am doing what? I will do nodal analysis at 0 plus. Very, very interesting. So now we are doing nodal analysis. Yes, nodal analysis at t equal to 0. Generally, mesh and nodal we did in steady state. But we can also do in transient state because no one can violate KCL or KVL at any instant of time. So I am doing for the first time nodal analysis in transient state. Chalo, sir, what I will do now? I will take this as reference. Let me take this as node voltage V. Now I'm writing the nodal equation. Okay, if I write the nodal equation, yes, what is the equation? This entire thing is only one junction, na, sir. This entire thing is only one junction. Minus 40, yes, minus 40 amperes. Okay, this is V by 6 plus V by 6. Okay, plus this is V minus 120 by 2. Yes, this is V minus 120 by 2. Okay, plus V by 3 plus V by 3 equal to 0. Okay, minus 40 plus V by 6 plus V minus 120 by 2 plus V by 3. Now, if I take LCM 6, okay, minus 240 plus V plus 3V minus 360 plus 2V equal to 0. So 6V is 600. So V is 100 volt. V is 100 volts. Okay, V is 100 volts. Okay, so please understand. V is 100 volts. Now you get V. So now I am finding KVL. So now I am writing what, sir? KVL to find VL of 0 plus. So first I will write a KVL. So if I write KVL, so what is the KVL? Minus 200. Yes, minus 200. Okay, plus IR. See, in this register IR, I is already 40 now. 40 amperes is in series now. 40 into 2 plus 40 into 2 IR. Okay, plus this is what we need to find, VL of 0 plus. Okay, VL of 0 plus plus this V, but node voltage is how much we got? Node voltage is 100. So the voltage across this 6 is also 100. So plus 100 plus 100 is equal to 0. So from that I am getting what? I am getting what? Yes, this VL of 0 plus. Yes, from that I am getting what? This VL of 0 plus. So this VL of 0 plus will be, yes, total, it is going to be 200 minus 180, 20 volts. Then I can say this di of 0 plus by dt is VL of 0 plus by L. But VL of 0 plus how much we got? 20. By L is how much? L is how much? He gave L how much? L is 1 millihenry, 1 milli. So di of 0 plus by dt is, yes, di of 0 plus by dt is 20 kilo ampere per second. 20 kilo ampere per second. Okay, na? 20 kilo ampere. So we got the third bit, sir. Wonderful. Now I also need IC of 0 plus. If I can somehow get IC of 0 plus, I will get dV of 0 plus by dt also. But Ohm's law, this IC is potential difference by path resistance. Now I am writing Ohm's law here. Also Ohm's law, from Ohm's law. What is that Ohm's law I can write? Yes, this IC of 0 plus will be, okay. Now what is IC of 0 plus? V minus 120 by 2. That is V minus 120 by 2. That is 100 minus 120 by 2, that is minus 10, minus 10. So then dV of 0 plus by dt, okay, yes, it will be how much? IC of 0 plus by C, okay, minus 10 by C. C is how much? 10 micro. So this is minus 1 megavolt per second, minus 1 megavolt per second, okay, minus 1 megavolt per second. Okay, minus 1 megavolt per second. Yes, please understand, minus 1 megavolt per second. Okay, minus 1 megavolt per second. So if it is minus 1 megavolt per second, yes, please understand, if it is minus 1 megavolt per second, yes, we got the two more answers. See, one is di of 0 plus by dt I got, and one is dv of 0 plus by dt also we got. Okay, minus 1 megavolt means, yes, it is releasing. Capacitor is releasing. That is the meaning there. Okay, na? Because IC direction is ulta. We took passive notation. I will follow strict notation, sir. I took first passive notation, but later answer came negative means, yes, answer came negative means actually capacitor is discharging. That is why it is voltage rate is decreasing. If it is charging, voltage rate across it is increasing. That is the meaning here. Okay, na? Chalo, finally, what else we want now? I of infinity and V of infinity. Now I am going to part 3 solution. Yes, part 3. Part 3 solution is, okay, future steady state. Future steady state, that is t tends to infinity. Now t tends to infinity, what is the change? This resistor has come again for DC, along with this resistor 6 ohm, again for DC, inductor short, capacitor open. Okay, so that is what happens here. Yes, what is going to happen now? Yes, again inductor short, but what extra has come? This 6 ohm and capacitor open. Okay, this is 200 volt, 2 ohm, 6 ohm, 3 ohm, 2 ohm. Okay, and this is I of infinity and this is V of infinity. Okay, so now what is I of infinity again? I of infinity is again how much? Total voltage by total resistance. That is 2 plus 6 in parallel to 3. That is 200 by 4, 50 amperes. And what is V of infinity? Voltage division rule, because 6 and 3 are in parallel. Na? So total voltage into same 6 and 3 parallel, because across this is across 6 and 3 parallel. 6 and 3 parallel become 2 by 2 plus this total resistance another 2. That is nothing but 100 volt. 100 volt. Okay. So this is the three problems, sir. So we got everything now. See, first I of 0 plus V of 0 plus we got from the previous steady state, that is past to steady state, these two. Then present transient state, first time we wrote circuit at t equals 0 plus, from that I got di of 0 plus by dt and dv of 0 plus by dt. I did nodal analysis at 0 plus, and then future steady state, I got I of infinity and V of infinity. Now understanding, just understanding I'm writing. Okay. First you look at current. Okay, just for understanding I'm writing. If you look at this inductor current, okay, if you look at this inductor current versus time, you see now where the inductor current is starting. Current was previously at 40 amperes. Inductor current was previously at 40 amperes. Now where it is reaching finally, inductor current was previously at 40 amperes, where it is reaching finally 50 amperes. So it was at 40 amperes, it reached 50 amperes. It is at 40 amperes, it reached 50 amperes. Okay, it was at 40 amperes, it reached 50 amperes. But in what way? Yes, because we don't know here direct formula whether it is underdamped, overdamped, or critical. What is the reason we don't know? Because those formulas what we got is valid only for series RLC. Here also this circuit will have its damping factor, undamped natural frequencies, etc. But that is not easy to find. That is why control system transfer function analysis Laplace we will start for such problems. But understanding is it will start at 40, it will reach 50. But you know, second order circuit, either three types of responses are there. Either it can go overdamped, yes, either it can go overdamped sluggish, critical damp faster, or underdamped much faster with oscillations. So one of this is answer. We don't know right now. Yes, one is answer. So one of this is correct. We don't know right now. One of this is correct right now, we don't know, but the rate at which it is increasing, see the initial rate at which it is increasing is how much? 20 kilo ampere per second. That is 20 kilo ampere per second. That is the understanding. Similarly, if you look at the capacitor voltage, everybody watch this. Capacitor voltage also, if you plot, yes. Now listen, initially where was the voltage? 120 volts. Initially it was at 120 volts. Now where it is coming finally? 100 volts. So it is discharging. It was initially at 120 volts. Okay, it is coming down to 100 volts. It is coming down to 100 volts. Okay, it was initially at 120 volts. It is coming down to 100 volts. Again, it can happen in three possible ways. Okay, again, it can happen in three possible ways. Either overdamped, okay, or critically damped, or underdamped. Okay, overdamped, critically damped, or underdamped. Again, one of this is correct solution. Yes, one of this is correct. Yes, one of this is correct. But it is discharging at what rate? Discharging at what rate? Yes, discharging at what rate? It is discharging at what rate? Discharging at the rate of, yes, -1 megavolt per second. Okay, this is -1 megavolt per second. -1 megawatt per second. So that is our understanding. But it is overdamped, critical damped, underdamped. Right now, I don't know because those formulas are not applicable here. Okay, na? But we can find by Laplace and transfer function. That is what very important. Okay, na? But one thing is sure, the characteristic equation is unique. That means if current is overdamped, voltage is also overdamped. If current is underdamped, voltage is also underdamped. Like that, it will be same. Okay. So now go through this problem, everyone. See, first problem was direct because it is a simple RL. I wrote the differential equation. From that, I got everything. Second problem is more challenging. Yes, we got I of 0 plus, di of 0 plus, and I of infinity. And that is what here. First, past state 0 minus, present transient state 0 plus. This is the first time we wrote this circuit. Okay. Then future state is t tends to infinity with 6 ohms added. Okay. Na? So now, if you understood this, now, sir, gate bit. I want everyone to try this. Find Vs of 0 plus, switch voltage at 0 plus. Please understand the question. Find the switch voltage at 0 plus. This switch is opening at t equal to 0. Okay, the switch is opening at t equal to 0. This is supply. V is supply. Okay, I'm asking this. What I'm asking, switch voltage at 0 place. Okay, I'm asking the switch voltage at 0 place. Chalo, I'm giving you 1 minute. Okay, I will give options also. V into R1 by R2. Second option, V into R2 by R1. Third option, V into R1 by R1 plus R2. V into R2 by R1 plus R2. Okay, find Vs of 0 plus. Okay, everybody find Vs of 0 plus. Chalo, see, Vs is the switch voltage. V is the supply voltage. Don't confuse. I need the switch voltage at 0 plus at the instant when it is opening. I'm giving you 1 minute try. I'm going to do now. Yes, everybody. Now see the solution. Everybody watch. See, to get this answer, I need to write the zero plus circuit. Okay. Now how to write the zero plus circuit? First, I need initial conditions. So first you should go to zero minus only first. Zero minus. Zero minus means previously switch was closed. Okay. Previously switch was closed. Then in DC steady state, capacitor is open circuit. Okay. And inductor is short circuit. These are the two memory elements. These are the two memory elements, that is inductor current and capacitor voltage. So in the previous DC steady state, okay, yes, we know for DC, the switch was closed, capacitor is open, inductor is short. Now I need the memory values. So what are the memory values? So I need this V of 0 minus, and I need this I of 0 minus. But if you observe, this is open, current cannot flow. So full current, okay, full current will flow through the inductor only. And that current is how much? That current is how much? V by R2. So this inductor current is V by R2. But what about the capacitor voltage? If you write a KVL, there is no voltage here. Na? If you write a KVL, there is no voltage. Or you write KVL like this also, you'll get 0. So that means in the previous steady state, inductor current is V by R2, but capacitor voltage is 0. That is the previous DC steady state. Now with these initial conditions, I am writing the 0 plus circuit. Now I am writing the 0 plus circuit. So if you write the 0 plus circuit, everybody watch. If you write the 0 plus circuit, okay. So first of all, capacitor short with initial condition, but luckily initial condition is not there. So what is the sudden change? Actually, the switch has opened. Here the sudden change is the switch has opened. That is what he is asking. Switch has opened. And 0 plus capacitor short with initial condition. Yes, capacitor short circuit, but the initial condition is not there now. Capacitor does not have initial condition. Then what about inductor? Inductor open with initial condition. Inductor is open with initial condition. Inductor is open with initial condition. Inductor is open with initial condition. Okay. Inductor is open with initial condition. Okay. So if it is V, this is R1, this is R2. Okay. Switch has opened. And this is inductor open with initial condition. But what is initial condition? Initial condition is V by R2. V by R2. Okay. Initial condition is V by R2. Okay. Now what I want, I need this Vs of 0 plus. I need this Vs of 0 plus. Okay, na? Yes, I need this Vs of 0 plus. Okay. Now simple, sir. Yes, this is the circuit at 0 plus. So capacitor short only because there is no initial condition, but inductor open with initial condition. So now voltage V equal to 0 plus is nothing but the voltage across this resistor only, na sir. That is current into resistance, but this current is already V by R2 only. That current is V by R2 only. So from Ohm's law, Vs of 0 plus, that is the question is asking, na sir. Vs of 0 plus is I into R. That is V into R1 by R2 is the answer. Because V is IR, I is already V by R2, V by R2 into R1 is V into R1 by R2. So what is the correct option? Yes, V into R1 by R2. That is the correct option. Okay, na? That is the real correct option. Okay, chalo. Now I'm giving another gate question. I want everyone to try this also. Okay, I'm giving another gate question, everybody. Yes, find di of 0 plus by dt. Okay, find di of 0 plus by dt. One ohm, 20 ohm, 20 ohm. This is 1 millihenry. This is 1 microfarad. And this is 100 volt. And I am asking the rate of change in this inductor. Okay. Chalo. Find di of 0 plus by dt. 1 minute I am doing, otherwise everybody is quick. Everybody quick. Try something, otherwise I will do. Yes, how to get this di of 0 plus by dt? See, I told you, sir, the rate of change of inductor current you'll get by Ohm's law, VL of 0 plus by L. Because this is also not a simple series purely or purely parallel. So you cannot write one differential equation and get it. So I have to use the initial conditions. But to use the initial conditions, first find it. So I'm first going again to t equal to 0 minus. I'm going to t equal to 0 minus state. T equal to 0 minus means previous steady state. In previous steady state, switch was open. When switch was open, this resistor is working. Okay, inductor for DC short, capacitor for DC open, capacitor for DC open, and this is now how much? 100 volts. This is now how much? 100 volts. This is now 100 volt. This is now 20 ohm. This is now 20 ohm. This is now 20 ohm. Okay. Now I need the initial conditions. 1 I of 0 minus 1 V of 0 minus. Okay. Now I'm finding these two, this and this. So what is I of 0 minus? 100 by 40? That means 5 by 2 amperes. And what is V of 0 minus? The voltage here is voltage across this only. I into R, that is 50 volt. That is 50 volt. Okay. Now with these two, I can now write the 0 plus circuit. Okay. Now with these two basics, yes, I can write the 0 plus circuit. Okay. What I can do now? I can write the 0 plus circuit. Okay, now everybody. Chalo. Now 0 plus circuit I'm writing. At t equal to 0 plus. What is the change that happened? The switch has closed. First of all, the change is the switch has closed. When switch has closed, this 100 ohm is not working. Then we know inductor open with initial condition. Yes. And capacitor also short with initial voltage. Capacitor is also short with initial voltage. Initial voltage. That is the meaning here. Okay. However, this supply is still 100 volts. This is 100. This is now 20 ohm. 20 ohm. Okay. Now this current is 5 by 2 amperes and this voltage is 50 volt. This voltage is 50 volt. Okay, 5 by 2 and 50 volt. Okay, now then what I want here, yes, please understand what I want is ulta state well, because he's asking di of 0 plus by dt, VL of 0 plus. I need this VL of 0 plus. VL of 0 plus. Okay. So now in that regard, this current is already how much? 5 by 2 amperes. And I'm writing a KVL. So if you write a KVL, okay, minus 100 plus IR. IR plus VL of 0 plus is 0. So from that, what is VL of 0 plus? VL of 0 plus is, yes, VL of 0 plus is 100 minus 50, 50. Once I got this, now conclusion, di of 0 plus by dt is VL of 0 plus by L. VL of 0 plus by L. Okay, na? Chalo, VL of 0 plus how much we got? Yes, 50. But L is how much? 1 milli. So that is 50 by 1 milli. That is 50 kilo ampere per second. See, this is the answer. Ulta state variable. So it's 0 plus ulta. What is the meaning of ulta state variable? Actually, in inductor, current is state variable. But what we are finding, voltage across inductor at 0 plus we are finding. That is why it is called ulta state variable. That is how I pronounce. Okay, na? That is the answer. So yes, when the circuit is neither pure series nor pure parallel, just by simple equation you will not get, sir. So build this 0 plus circuit. Okay, na? So now I'm giving another ISRO bit. Yes, ISRO. It also came in so many exams. This model. Find I1 of 0 plus, I2 of 0 plus, I3 of 0 plus. Okay, these are the mesh currents. Now see, very interesting. Mesh currents at 0 plus I'm asking. I'm asking something different. Mesh currents at 0 plus. $90 volt, 2 ohm, 4 ohm. Okay, this is 2C, C and L. And here switch is closing at t equal to 0. But I'm asking this I1, I2 and I3. Mesh currents at 0 plus. I'm asking mesh currents. Shall everyone write the 0 plus circuit? Everyone write the 0 plus circuit first. Then mesh currents at 0 plus will get. Yes, everybody. See now, I want the mesh current at 0 plus. Now to get the mesh current at 0 plus, I will write the 0 plus circuit and write the mesh equations. So what I will do, I will write the 0 plus circuit and write the mesh equations. That's the meaning here. Okay, I will write the 0 plus circuit and write the mesh equations. Okay, na? Chalo, first to get that, I am writing first 0 minus t equal to 0 minus. 0 minus switch was open, sir. When switch was open in previous DC steady state, everyone watch. When switch was open in previous DC steady state, yes, here inductor is short, capacitors are open. Okay, both capacitors are open. That is the previous DC steady state. Okay, inductor is short, both capacitors are open. Okay, now switch is also open. Okay, this is 90 volt, 2 ohm, 4 ohm. Okay, yes, both capacitors are open and inductor is short. Now I need the memory elements. So what are the memory elements? One is I of 0 minus, and this is V of 0 minus, and this is also V of 0 minus. Now clearly, if you observe, the only resistance seen by 90 volts is 2 plus 4, 6. So this current is automatically 90 by 6, 90 by 6, which is 15 amperes. Okay. Now when 15 amperes is going through 4 ohms, it is become 15 fours or 60 volt. Yes or no? Now the 60 volts will divide across these two series capacitors. Yes or no? The 60 volts will divide. Then voltage division rule. This voltage will be total voltage into in capacitors opposite. Opposite, this is how much? 2C by some 3C. That is 40 volt. 40 volt. Now, if this is 40 volt, automatically this will be how much? 20 volt. This will be how much? 20 volt. Okay. So with this information, I am now writing the 0 plus circuit, T equal to 0 plus circuit. Now 0 plus, what is the change? The switch at the center got closed. Okay. What is the sudden change? First, everyone should observe. The sudden change is switch got closed. This switch got closed. Okay. These are registers as it is I am writing. But the change is this switch got closed. This switch got closed. Then we know capacitor short with initial condition, inductor open with initial condition. Here also capacitor short with initial condition. So there are three memory elements, are 2 capacitors, 1 inductor. This is 90 volt, this is 2 ohm, 4 ohm. But here capacitor short with initial voltage. What is the initial voltage? 20 volt. Okay, this is how much? 40 volt. Okay, now inductor open, I did not show. Yes, inductor is open, it is understood. But what is the initial current? 15 amperes. 15 amperes. So now I want these currents, that is I1 of 0 plus, okay, I2 of 0 plus, because he is asking this only because it is a 0 plus circuit. I3 of 0 plus, yes. So for that I am writing the mesh equations. Now I am writing mesh equations at 0 plus, mesh equations at T equal to 0 plus. That is called transient state mesh analysis, not steady state mesh analysis. But KVL, KCL, no one can violate. So if I write the mesh equations, first minus 90 plus 2 I1 of 0 plus 4 into I1 of 0 plus minus I2 of 0 plus, okay, plus super mesh plus 40 is equal to 0. That is the first equation. Second equation, if I go 4 into I2 of 0 plus minus I1 of 0 plus, okay, plus 20 equal to 0. Plus 20 equal to 0. That is second. Third difference, that is I1 of 0 plus minus I3 of 0 plus equal to 15. That is 3. Now solve 1, 2 and 3. Chalo, solve 1, 2 and 3 we get. Yes, we get these values. Yes, one is I1 of 0 plus, one is I2 of 0 plus, and finally I3 of 0 plus. Okay. Yes, you solve this, you will get the answer. Yes, if you solve this, yes, you will get the answer. I did it already, sir, so I'm copying from there. Don't misunderstand. Okay. I don't remember. See, everything I cannot remember. So I did this and yes, we get this answers as, yes, this is now 15 amperes we are getting. This you are getting as 10 amperes and this is 0 amperes. Interesting. Remember. Please observe, sir. First I got initial conditions. Everybody, first I got initial conditions. Okay, na? Yes, first I got initial conditions. Okay. Then with this initial conditions, I got 0 plus circuit. Now I am doing mesh analysis at 0 plus. Okay, mesh analysis at 0 plus. So answers are, the mesh currents during transient state is I1 of 0 plus is 15, I2 of 0 plus is 10, and I3 of 0 plus is 0. Okay, 0. Okay. Another gate question for electrical. Find di of 0 plus by dt. This was the question given. Get recent 2019. 2 marks. I don't think it's even 2 marks, but he gave a very easy question. He gave. This is given as 1 Henry and is closing the switch at t equal to 0 and is asking this current I. Chalo, 1 minute, everybody, 1 minute. Please try to do 1 minute, everybody. Try to do 1 minute. Yes, everybody see now. Again, I want dI of 0 plus by dt. Now, how to get this? I need a ulta state variable, VL of 0 plus. So first I am going to 0 minus. Here also, sir, first previous steady state. Previous steady state switch was open. Okay. Yes, this switch was open. Yes, previous steady state switch was open. Okay. Yes, this switch was open. Okay. But for DC, inductor short. So this is 3 volt, 1 ohm, 2 ohm, 3 volt. So now this becomes I of 0 minus. It becomes I of 0. What is I of 0 minus? 3 by 2. 3 by 2 amperes. Yes or no? Because current only go from there. Because in the previous DC steady state, inductor short. Now with this information, I'm writing the 0 plus circuit. Okay, now I'm writing T equal to 0 plus circuit. What is the change that happened? First of all, this switch has closed. Okay, the left side circuit also came. This switch has closed. Now inductor open with initial condition. That is a change that happened actually. Okay, left side, this extra voltage came now. Switch has closed in the left side. Yes. So this is 3 volts, switch has closed. Here also 3 volts, switch has, so this is closed. And here it is now 1 ohm, this is 2 ohms. And now inductor with initial condition. But what is initial condition? 3 by 2 amperes. Initial condition is 3 by 2 amperes. Okay. So now what I want, I need this ulta state variable. That is VL of 0 plus. VL of 0 plus. Okay. So now I'm doing what? Nodal analysis. See why I will take nodal. Okay. I'm finding now VL of 0 plus. Now if I write the nodal equation, see VL of 0 plus minus 3 by 1 plus 3 by 2 plus VL of 0 plus minus 3 by 2 equal to 0. See, VL of 0 plus minus 3 by 1, this is already 3 by 2 amperes. VL of 0 plus minus 3 by 2. So if I observe LCM 2, 3 VL of 0 plus, okay, this will be 6. So VL of 0 plus is 2. Then di of 0 plus by dt is VL of 0 plus by L. That is 2 by L. Now what is L? L is 1. That is 2 ampere per second is the answer. Okay, 2 ampere per second. Chalo sir, now we are coming to solution. Now see sir, what everyone, now quick review what we did. Everybody should listen now. So see, yesterday we gave the formulas for second order source tree. Yes or no? We just gave the formulas and understood the mathematics. Okay, I understood the mathematics for series and also parallel. Okay, and I took some problems to only give the formula meaning. Okay, and also one time constant concept. Then we did not do solution. Then we came to step response second order. Here also only mathematical meaning I give. Okay, that is solution for category 3 source free. I attached here in the natural part. Then this became solution to category 4 including steady state step response. Okay, then parallel RLC also we did. But I told at the conclusion that yes, in determining the complete solution to the second order circuits, here it is a big challenge to find the constants A1, A2 na? Yes, the big challenge is to find constants A1, A2. Hence, what we require, we need to determine initial conditions. Yes or no? Now we are ready with initial conditions, sir. See, we did know a lot of problems on initial conditions now. Okay, we did a lot of problems on initial conditions. Yes or no? Chalo, now we know how to find initial conditions. Okay, chalo, now once we are ready to find initial conditions, now I am writing the solution. Chalo, now we are coming to combination of category 3, 4, 5. Yes, solution to complete solution to second order circuit. I will write like this: complete solution to second order circuits. Complete solution to second order circuits. We are writing complete solution to second order circuits. Please understand what I'm trying to do. Okay, we are writing complete solution to second order circuits. That is combination of category 3, 4, and 5. So here we are mixing category 3 formulas, category 4 formulas, and category 5. Because initial conditions also we require all combined. Chalo, I'm going with the first major question. Find V of t for all t greater than 0. Everybody watch this question, please. $30 volts are equal to 5 ohms, 1 Henry, 1 by 4 farad, 1 ohm, and switch is getting opened at t equal to 0. Okay, Find V of t for t greater than 0. Okay, this is V. Everybody watch this question. I'm going to start now. Everybody watch this question. I'm going to start now. Yes, everybody see. Now here switch is getting opened. Everybody should watch this. Here switch is getting opened at t equal to 0 plus. Very good, sir. So many are giving answers. I'm very, very happy. Very happy. Really happy, sir. At least, there are some 20 to 30% students who are serious, sir. Really serious. Please continue this preparation, sir. You will get rank this time. Very good rank you will get. Don't worry. Okay, because of COVID pandemic, online, offline, whatever it is, sir, the sincere students who are doing their bit and part will 100% get rank. All my good wishes and blessings are there with you. Continue, sir. Don't stop now because this is the critical state. November, December, January is like ultimate. Now onwards, you don't waste even 1 minute. Okay, you will get rank. Pakka rank. So many, sir. Overall, so many stopped preparation. So many did not clear BTech properly. Don't have backbone and fundamentals. But you can do it. Okay, competition is less, but you can take advantage of it. Children, listen, everybody. Yes, find V of t for all t greater than. First of all, here switch is getting open. Yes or no, switch is getting open, so 1 ohm will leave the circuit. When switch is getting open, 1 ohm will leave. It becomes a series RLC. Yes, it becomes a series RLC. Second order, na. Now, still, even though the switch is opening, voltage source is still available, na. Even though the switch is opening, voltage source is still available. So this comes under step response or source free. This comes under step response. That is first thing we have to observe. Why it is step response? Why it is step response? Yes. The reason it is step response is even though the switch get open, yes, even though the switch get open, source is still available. So this comes under step response. Yes or no? Yes, this comes under step response. Okay. Chalo. Now, what is the order? But two are there, LNC are there. So it is second order. No doubt, second order. And it is a standard series RLC. Standard second order, and it is a standard series RLC. Okay, standard series RLC. So standard series RLC. So our formulas are applicable. Our omega naught, alpha, etc. Formulas are applicable. Are applicable. If it is neither pure series nor pure parallel, today we will do that is by Laplace. So because it is standard series RLC, our formulas are applicable. But what is the state variable? Is asking voltage only. He is asking state variable voltage. Chalo, is asking state variable voltage. Okay, na? Chalo, now in that regard, everybody, now in that regard, chalo, first we know this total response V of t is V steady state plus V transient state. Yes or no? But first V steady state will find. V steady state is at t tends to infinity. T tends to infinity. Okay, V steady state is at t tends to infinity. Now, if you go to t tends to infinity, everybody, if you go to V tends to infinity, inductor short, capacitor open. Inductor short, capacitor is open. Inductor short, capacitor open. Okay, that is 30 volts. This is 5 ohms. And now, yes, this is our V of infinity. Now, current cannot flow here. Full voltage will come. V of infinity is 30 volts. Yes, steady state value we got. V of infinity we got. But V transient of t. Now I'm writing. Yes, but V transient of t. But V transient of t depends upon, yes, depends upon RLC values, where alpha is R by 12 because it is series RLC, this formula is applicable, R by 12. But after opening the switch, what is R5? 5 by 2, L is 1. So that is 5 by 2 into 1. That is 2.5 omega naught. Omega naught is 1 by root LC, 1 by root LC. See, after the switch got open, what is LC? L is 1, C is 1 by 4. L is 1, yes, C is 1 by 4. That is 2. So clearly alpha greater than omega naught. Alpha greater than omega naught. What are these? Overdamped. Chalo sir, overdamped response. Now in overdamped response, first let us find S1, S2. See, in overdamped, the nature of response for V transient is like, okay, e power minus alpha t, sorry, in overdamped, na sir, let me correct it. In overdamped, because here alpha greater than omega naught, overdamped. Overdamped, what is it? A1 e power S1t plus A2 e power S2t. But what is S1, S2? S1, S2 is minus alpha plus and minus root of alpha square minus omega naught square. So calculate this is minus 2.5 plus and minus root of 2.5 square minus 2 square. You do it here. Yes, we got this. Yes, these roots are going to be now -4 comma -1. Then I can write first the total response look like total response is now V steady state how much 30 plus V transient is in this form. Okay, V transient is in this form. So total V will be V steady state is 30 plus V transient. Okay, A1 e power S1 is -40 plus A2 e power S2 is -1t for all t greater than or equal to 0. Chalo, this is our main equation. Chalo, sir, this is our main equation, sir. But here, what is the challenge? Please tell me. The challenge is to find what? A1, A2. Now to find A1, A2. Yes, I'm writing here. Now to find A1, A2. Now to find A1 and A2. Okay. Let us find initial conditions. Let us use, okay, use initial conditions. Initial conditions. What is the idea then? The idea is, yes, the idea is first I will find V of 0. Okay, V of 0 plus is V of 0 only. Na? Yes, V of 0 minus is V of 0. Okay, first I will find V of 0. So if you put V of 0 at t equal to 0, e power 0, 1, e power 0, 1, A1 plus A2 plus 30 is 1 first. A1 plus A2 plus 30 is first. Then second is, I will also find dv of 0 by dt or dv of 0 plus. That is understood, na? Yes, if you can find these two, now I'll differentiate and put t equal to 0. Here also I will differentiate and put t equal to 0. Okay. Yes, if I differentiate and put t equal to 0, yes, that is what was happening. It was differentiation and putting t equal to 0. Okay. Yes. Now, if I can get these two, I will get it. So how to get these two? This is from category 5 initial condition problem. This is from initial condition problems. Initial condition problems. This is from initial condition problems. Okay. So first to get this, I am now going to t equal to 0 minus circuit. Okay. If I go first t equal to 0 minus, if I go t equal to 0 minus, what was 0 minus? Everybody watch. 0 minus means previous steady state. Previous steady state switch was closed. Yes, previous steady state switch was closed. Again for DC, inductor short, capacitor open. Okay. So if I go to the previous steady state, switch was closed. Okay. Now this is there. Again, inductor is short, capacitor is open, but this 1 ohm was there. This 1 ohm was there. 1 ohm. Okay, this is 30 volt. This is clearly 5 ohm, and this is 1 ohm. Okay, now this is, yes, I of 0 minus, and this is V of 0 minus. So if I go to I of 0 minus, what is this? 30 by 6, 5 amperes. What is V of 0 minus? 5 ones are 5 volts. 5 ones are 5 volts. So now we got this V of 0 minus now. So this itself is, yes, this V of 0 minus itself is V of 0. Now use it in the main equation. Chalo, if I use this in the main equation, now I'm putting here, put t equal to 0, substitute this condition here. So this V of 0 is, okay, 30 plus A1 plus A2, because e power minus 0, e power minus. But what is this V of 0? We got 5. Yes or no? V of 0 we got 5. So I can say A1 plus A2 equal to minus 25. This is the first equation. Okay, first equation. Then I want dV of 0 by dt. How to get dV of 0 by dt? Everyone tell me how to get IC of 0 plus by C. IC of 0 plus by C. So I'm writing the, yes, IC of 0 plus by C. So here I'm writing T equal to 0 plus circuit. Okay, I'm writing what here? T equal to 0 plus circuit. Chalo, I'm writing T equal to 0 plus. Now, if I write the T equal to 0 plus, everybody observe what is the change that happened. That switch has opened. The switch has opened. So first of all, switch has opened. Very good. Switch has opened. Now here, inductor with initial condition. Okay. And capacitor also with initial condition. Capacitor also with initial condition. Okay. Yes. This is now 30 volts. This is how much now? 5 ohms. This 1 ohm is gone. Inductor with initial condition and capacitor with initial. But what are the initial conditions? We got 5 ampere and 5 volt only. Na? This is 5 ampere and this is 5 volt. Now I need what? I need this IC of 0 plus. Then only I will get this dV of 0 plus by dt. Na? So what is IC of 0 plus? Direct observation, sir. Here current source is in series to all the elements. Current source is in series. So this is clearly 5 amperes. Now again, so now from this I can find dV of 0 plus by dt is IC of 0 plus by C. Okay. Yes, IC is C. C is how much? 1 by 4. Yes or no? C is in the question is how much? 1 by 4. So if I use that, that is 20 volt per second. Now use this in the main equation. Yes, use this in the main equation. Use this in the main equation. Now to do that, first I will differentiate the main equation. So if I differentiate the main equation, okay, first differentiate, okay, I will differentiate. This dv of t by dt will become what? This dv of t by dt is what? First of all, this 30 is constant 0, but this become minus 4a1 e power minus 40, minus 4a1 e power minus 40, and this becomes what? Minus a2 e power minus t, minus a2 e power minus t. Now put t equal to 0. Now if you put t equal to 0, yes, now if you put t equal to 0, yes, dv of 0 by dt, how much we got? 20 volt per second. 20 is equal to minus 4a1 minus a2. That is second equation. Chalo, see, we got first equation here. We got second equation here. Okay, we got the first equation here. Yes, first equation here, and also second equation here. Now solve. Yes, now solve 1 and 2. Solve 1 and 2. We get. Chalo, now solve 1 and 2. We get. First of all, if you add 1 and 2, na sir, a2 will cancel. A2 will cancel. So, yeah, a2 will cancel na. So minus 3a1 is minus 5. So minus 3a1 is minus 5 means a1 is, okay, 5 by 3. Now if a1 is 5 by 3, substitute here. If a1 is 5 by 3, a2 is minus 25 minus 5 by 3, minus 80 by 3. a2 becomes minus 80 by 3. Chalo, now we got the total solution. So complete response is, now substitute everything, sir, everything, that v of t is equal to, okay, v steady state, that is 30, yes, 30 plus a1 5 by 3 e power minus 40 plus a2 minus 80 by 3 e power minus t for all t greater than or equal to 0. Okay, we get this. So that is what we get. Okay, 30 plus 5 by 3 power minus 40 minus 80 by 3 power minus t for all t greater than 0. Now if you plot voltage versus time, yes, response. Now if you plot voltage versus time, yes, if you plot this voltage versus time, now to understand, see, now to understand where it is starting, previous steady state, where it is starting, we are observing voltage now as per the question. Previous steady state voltage was at 5 volts. Okay, previous steady state voltage was at 5 volts. Where it is reaching 30 volts, infinity is 30 volts. So it is starting at 5 volts, it is reaching 30 volts. Okay, first of all, if you observe, yes, it is starting at 5 volts. Yes, it is reaching 30 volts. Okay, it is starting at 5 volts, but it is reaching 30 volts. Yes or no? That is the meaning. Okay, that is all we got. So it starts at 5 volts, but it reaches 30 volts. Okay, with an initial rate of change of how much voltage? 20 volt per second. With an initial rate of change of 20 volt per second. But in what way? It is going in overdamped way. It is what way? In a overdamped way. So yes, it starts at 5, reaches 30 with an initial rate of yes, 20 volt per second, but in an overdamped way, sluggish. Overdamped is sluggish. Okay, this is overdamped. Okay, na? So please understand everything. I will review now. Everybody see this. I am going to review now. 1 minute. Okay, see, sir, this is the first problem we did on second order complete solution. It is a very big problem, sir. But here, even though the switch is opening, but voltage source is still available, this comes under step response only, and it is second order series RLC, and state variable is voltage. So with respect to that, total response is forced plus natural. Okay, final value we got, but natural response depends upon RLC. Okay, based on RLC, it is overdamped. Now this is the nature of the solution that looks like. Okay, now here A1, A2 is the big challenge. For that, initial conditions we used 0 minus, we got V of 0, and from 0 plus we got dV of 0. So substitute both, we get two equations, and we got the answer. Okay, that is how we got the complete answer. Okay, that is how we got the complete answer. That is wonderful, wonderful question, sir. Everybody, wonderful question here. Okay, now I'm giving homework, sir. Everybody, homework for you. Homework. Okay, in the above problem, in the above problem, find, yes, in the same above problem, find again v of t for all t greater than or equal to 0. Okay, if a bit r equal to 4 ohm and b bit r equal to 1 ohm. Please observe this, sir. See the same problem. What you do, this r equal to 4 ohm you make and r equal to 1 ohm also you make. Then you will get the other two cases. That is, you will get what are the other two cases you will get? Yes, you will get the other two cases. That is critically damped and under damped also you will get. Okay, do this as homework. Okay, do this as homework. Okay, when doubt session is there, that time I will ask. Okay, now, Chalo, now I'm giving another question here. Yes, another question. Find I of t for all t greater than or equal to 0. Find I of t for all t greater than or equal to 0. This level we understand now, sir. Then it is done. Second order is done. This is 8 amperes. 1 Henry, 1 by 4 Farad, 10 ohm, 10 ohm. Here switch is closing at t equal to 0. And moreover, this is 20 u of minus t volt. Please understand. And is asking this current I. Solution for current I. Okay, everybody watch this question. Find I of t, complete expression for current I of t for all t greater than 0. Okay. Just observe, I'm going to start the solution now. Okay, now see this. Here two things are happening in one shot, sir. What are the two things? First of all, switch is getting closed, and moreover, this voltage source is suddenly becoming 0 at t equal to 0. Because this is 20 u of minus t, na, sir. What is the meaning of 20 u of minus t? 20 u of minus t means this 20 volts is suddenly becoming 0 at t equal to 0. So here two things are happening in one shot. First of all, switch is closing at t equal to 0, and this voltage is suddenly becoming 0 at t equal to 0. Please understand. Okay, switch is getting closed at t equal to 0, and voltage source is also becoming 0. But though this voltage source is becoming 0, but by closing the switch, this current source is still available now. Though this voltage source is becoming 0, but by closing the switch, current source is still available. So this comes under step response only. Please understand why it is step response. Why? Because current is still available. Okay. And what is the order? S2 inductor, 1 inductor, 1 capacitor, 2 energy storage elements. Second order. But see, sir, now once the switch is closed and voltage source becomes 0 at t greater than 0, switch is closed and voltage source becomes 0, then these 10 and 10 become parallel 5 ohms. This voltage source is shorted because it is 0 and switch is closed. 10 and 10 become parallel 5. So it becomes a parallel RLC. It becomes a parallel RLC. And state variable is asking is current only. Now we know Now we know this expression for current I of t is like I steady state plus I transient state. Okay, I steady state plus I transient state. Okay, first I steady state. Now I steady state is at t tends to infinity. I steady state is at t tends to infinity. Now if I go to t tends to infinity, everybody, yes. So here inductor is short. Okay, inductor is short. Okay, infinity I am going, sir. Switch has closed. Capacitor is open. And that voltage source also becomes zero, na? Short it. So this is our final circuit. Infinity circuit directly I am writing. This is DC final steady state. This is 8 amperes. This is 10 ohms and 10 ohms. But for DC inductor short capacitor. Now I need this. Yes, now I need this I of infinity. I need this I of infinity. But here this is shorted, this is shorted. Current cannot flow there. Current will only flow here. And this current is directly 8 amperes. So I of infinity is 8 amperes. We got this. Okay. DC steady state value we got. But I transient of t depends upon RLC. Depends upon RLC, where alpha here is 1 by 2 RC. Parallel, na sir, 1 by 2 RC. So that is 1 by 2. What is R now? See, once the switch closed and voltage source becomes 0, once the switch closed, voltage source becomes 0, R become 10 in parallel to 10. R become 10 in parallel to 10 into C. But what is C? But what is C? C is 1 by 4. C is 1 by 4. So alpha is 2 by 5. And what is omega naught? Omega naught is 1 by root LC. 1 by root LC. Okay, 1 by root LC. Okay, L is 1, C is 1 by 4. L is 1, C is 1 by 4. Okay, that is 2. So clearly here, alpha less than omega naught. Alpha less than omega naught. So alpha less than omega naught is clearly underdamped. Underdamped. Okay, alpha less than omega naught is underdamped. Okay, alpha less than omega naught is what? Underdamped. Okay, if alpha less than omega naught, it is underdamped, everybody. Then the solution, then I transient of t will be like e power minus alpha t a1 cos omega dt plus a2 sin omega dt. This is very interesting. But what is omega d? Omega d is root of omega naught square minus alpha square. That is root of omega naught square 4 minus this is 4 by 25. So this becomes omega d is called damped frequency. That is root of 96 by 25. Okay, it is root of 96 by 25. Okay, you will get something like root of 96 by 25, and that you get something around okay, something around 1.96 radians per second. This you check it, sir. Okay, 1.96 radians per second. So now I will write this total response look like this. Total response is like this I of t is equal to first I steady state. I steady state, how much we got? 8. We got 8 plus I transient state. I transient state is like this, na? E power minus alpha t. But what is alpha? 2 by 5, na? So e power minus 2t by 5 into yes a1 cos omega dt. A1 cos omega d. What is omega d? 1.96. 1.960 plus a2 sine 1.960. Yes, for all t greater than or equal to 0. Now again, what is the challenge? The challenge is to find a1, a2. So use initial conditions. Use initial conditions to find a1 and a2. What is the idea then? First to find I of 0. Second to find di of 0 by dt. Di of 0 by dt. Okay. One is I of 0, one is di of 0 by dt. Okay, these two we have to find. Now to find this, first I'm going to t equal to 0 minus state. Now t equal to 0 minus, everybody watch. This switch was open and voltage was there. Okay, switch was open. Yes, you please understand this switch was open. But DC steady state inductor short. This switch was open and their voltage source also was there. And capacitor is also open for DC. Switch was open and voltage was there. So this is still 8 amperes. This is 10 ohms. 10 ohms. This is 20 volts because in the previous steady state voltage was there. Na? T equal to 0 minus means previous steady state before 0, this 20 volts DC was there. Capacitor is open. Switch was open, inductor short because of 8 amperes. Okay, that is the meaning here. Now I need the memory values. 1, I need this I of 0 minus, and 2, I need this V of 0 minus. So if you observe what is I of 0 minus, again 8 amperes only. And what is the V of 0 minus? See now, these 10 and 10 become series across 20. Voltage division rule. This voltage will be total voltage into same by sum. But because both are 10, it will be divided into equally. 10 volts will come. Out of 20, this 10 series, so you'll get here also 10 volts. Because out of 20, 10 volts will come here, 10 volts will come here. Yeah. So now use this. Yes, now use this. Use this. Use this. Okay, use this. Please understand, use this. Okay, now if you use this, chalo, put this in main equation. I will put this in main equation. If I put this in main equation, this is 8 equal to 8 plus e power 0, 1, okay, cos 0, 1 and sine 0, 0. So that implies A1 is 0. Yes. See, use this initial condition. I of 0 minus is I of 0 plus, na sir. That is I of 0 only. Because inductor will not allow sudden change in current. If you put here in this main equation, this I of 0 is 8 equal to 8. E power 0, 1, cos 0, 1, sine 0, 0. So A1 plus 8 is 8. So A1 is 0. A1 is 0. A1 is 0. Okay, na? A1 is 0. Okay, A1 is 0. Okay, na? That is the first thing. That is the first thing. A1 is 0. Okay. Now, what is Gopalakrishna? Why are you raising your hand? Gopalakrishna, what is your problem? Gopalakrishna, any doubt? Okay, so don't raise your hand in between. It creates a problem in the screen and every time I get confused. Okay, now see here everyone. So I got A1 as 0. Now second equation is to get the di of 0 plus by dt. For that I will go to the 0 plus state. So if I go to t equal to 0 plus, what are the changes that happen? Two things. One is switch is closing and voltage also becomes 0. Okay, first of all, switch is closing. Yes, switch is closing and voltage also becomes 0. So first of all, inductor open with initial condition. The switch got closed and capacitor acts as short with initial condition. Short with initial condition, and this voltage source also vanished. So this is the 0 plus circuit. So this is clearly 8 amperes. This is also 8 amperes. Okay. Then automatically this is how much? Okay, this is how much now? Yes, if you observe everybody, this is clearly how much now you'll get. This is now 10 ohm. This is 10 ohm given. And this initial voltage, what is the initial voltage across capacitor? That is also 10. 10. Okay, that is also 10. Okay, now so this is what 0 plus circuit, because switch has closed, voltage has become 0, inductor open with initial condition, capacitor short with initial voltage. Now I want what? See, I need what? I need di of 0 plus by dt. I need di of 0 plus by dt. I need di of 0 plus by dt. That is V. That is nothing but VL of 0 plus by L, na. That is VL of 0 plus by L. VL of 0 plus by L. So I need it. So directly from observation, what is VL of 0 plus? That is 10 volts. 10 volts. Okay, 10 volts. That is VL of 0 plus by L. Okay. Okay, that is VL of 0 plus, that is 10 volts. Okay, so now use this. Now I can find di of 0 plus by dt is VL of 0 plus by L. That is nothing but 10 by L. L how much I took? 1. So that is 10 ampere per second. Now use this in the main equation. Chalo, first to use this, first let me differentiate this. Everybody, big equation. I have to differentiate this big equation, sir. Chalo, first let me differentiate this di of t by dt. Okay, if I do that, di of t by dt, if I do, okay, first is 8, differentiation of constant is 0. Now uv dash e power minus 2t by 5 into, yes, uv dash, cos is minus sine, minus 1.96 a1 sine minus 1.96 a1 sine 1.960. Then sine is cos na, plus 1.96 a2 cos. Okay, plus 1.96 a2 cos 1.960 plus vu dash plus vu dash. This is already a1. Okay, this is already a1 cos 1.960 plus a2 sine 1.960. Okay, 1.960 into differentiation of this exponential term. Okay, minus 2 by 5 e power minus 2t by 5. Minus 2 by 5 e power minus 2t by 5. Now put t equal to 0. Put t equal to 0. Okay, put t equal to 0. So this di of 0 by dt is how much? 10. 10 is equal to e power 0 1. Yes, e power 0 1. This become minus 1.96 cos, put t equal to 0 na sir, e power 0 1 sine 0 0 cos 0 1. So this is 1.96 a2. Okay, now here also if you put cos 0 1 sine 0 0, but e power 0 1 na minus 2a1 by 5, minus 2a1 by 5. This is 2. So first equation a1 is 0, second equation 2. Now solve 1 and 2, solve 1 and 2. See, a1 is already 0, a1 is already 0. Now if you put here, automatically a2 will be 10 by 1.96, that is 5.1. Chalo, 5.1. We get this. Chalo, a1 a2 we got now. Final answer. So complete response is this I of t is. Okay, now this is 8. You look at this 8 plus 8 plus, okay, this is 8. Now a1 is 0 means cosine term is missing, but a2 is there, 5.1 sine term is there. So 5.1 e power minus 2t by 5. Okay, that is plus 5.1 e power minus 2t by 5. 5.1 e power minus 2t by 5 sine 1.960. Okay, sine 1.960, sine 1.960 for all t greater than or equal to 0. For all t greater than or equal to 0. Okay, so a2 e power minus alpha t sine 1. So now if you understand, see, if you plot this, see, if you plot this to understand, see, very, very interesting conclusions are, watch this please. Okay, now if you look at the complete solution, where was the current before change? Before change at 0 minus, the current was at 8 amperes. Current through inductor we are watching now, the current was at 8 amperes. Finally where it is reaching, that also 8 amperes. See, previously it was at 8 amperes, now also it is reaching 8 amperes, but don't say transient did not happen. Previous steady state 8, next steady state also 8, but don't say current is not undergoing transient. The current is transient where it changed initially at what rate? 10 ampere per second, 10 ampere per second, but in what style? In what style it went in underdamped style, underdamped. So it starts at 8, reaches 8. Please understand the meaning. It starts at 8 and reaches 8. Please understand. It starts at 8, reaches 8. Okay, it starts at 8, reaches 8, but initial rate is 10 ampere per second, but in underdamped style. In underdamped style. That is outstanding concept. It starts at 8, reaches 8, but it went underdamped way. You put in this equation also, sir. Put t equal to 0, sine 0, 0, 8 only. Put infinity also, e power minus infinity 0, again 8 only. But in between this response will come. Okay, these two examples will give the complete solution to second order. Okay, complete solution to second order. Okay, chalo, now we will take a break of half an hour. Come back by 9:50. Then we will start AC transients and Laplace, sir. Chalo, come back by 9:50. Yes, everybody, are you back? Please raise your hand. Imtiaz, these are very big questions in IES conventional, but what sort of questions came in GATE and how to do them in 1 minute, 2 minutes, I will teach in Laplace. Don't worry. Okay, Imtiaz was asking, sir, such big problems, is this IES mains or GATE? Actually, in GATE, he will give such bits which are so simple that we can do in 1 minute or 2 minutes. Okay, na? And how to do them in Laplace, I will teach you. But as of now, they are like conventional models only, but covering all the three categories together. Okay, na? We have covered all the three categories together. Okay, na? So one standard series RLC I took. Yes, one standard series RLC I took. Okay, na? And overdamped case. Okay, overdamped case I explained with everything. And this homework, please try to do. And then standard parallel RLC I took, which is underdamped case. Okay, na? Yes, all this we do. Okay, na, everybody. Now I'm going further, sir. Everybody, I'm going further. Yes. My question is, find I of t for all t greater than or equal to 0. One by 4 farad, 1 Henry, 2 ohms, switch is getting opened at t equal to 0. 1 ohm, 3 ohms. And I need the expression for current. And this is 30 volts. So everybody watch this question. I'm going the solution now. Yes, I'm going with solution. Now see this. Here switch is getting open. So step response or source free. This is source free. Yes or no? Source free. Because switch is getting open, source free. And then this is second order. Why it is second order? Both L and C are working together and interacting, and it is a series RLC. Series RLC, and is asking state variable as current only. Now we know, because it is source free, steady state value is 0. I steady state is 0, but only I transient exists. I transient exists, and it depends upon RLC. Depends upon RLC. RLC. Let us see that. Now, because it is series RLC, once you open the switch, this becomes a see 2 ohms also is waste, na sir. Once you open the switch, 2 ohms also waste. It becomes a series RLC. Here alpha is R by 2L. But what is this total R? 3 plus 1 by 2 into L. Okay, that is 4 by 2. It is 2. Alpha is 2. Okay, that is 3 plus 1. And omega naught. What is omega naught? 1 by root LC. 1 by root LC. That is also 1 by root. L is this, C is this. That is also 2. So here alpha equal to omega naught. This is critically damped. Yes, critically damped. Now critically damped, the nature of the response will be this I transient of t is of the form e power minus alpha t a1 plus a2t. So this I transient of t is of the form. What is alpha? We got 2 na. Alpha we got 2 na. So e power minus 2t a1 plus a2t. Chalo, my challenge is to find a1, a2. Again, use initial conditions. So what is the idea then? First find I of 0 and then yes, I of 0. So I total only. See, I transient is I total here because steady state is 0 na. I transient is I total because steady state is 0. That is why I mentioned here. Here steady state is 0. Only transient exists. So I of t is I transient only. Okay na. Chalo, I of 0 we need to find, and second we need to find di of 0 by dt also we need to find. Now for these initial condition problems. So first I am going at t equal to 0 minus. If I go to t equal to 0 minus, everybody watch. If I go to t equal to 0 minus, previous steady state, yes, switch was closed. Yes, switch was closed. In previous DC steady state, when switch was closed, capacitor is open, inductor is short. This is the previous steady state. This is 30 volts, 2 ohms, 1 ohm, 3 ohm. And this is our I of 0 minus. So what is I of 0 minus? 30 by 3, which is 10 amperes. 30 by 3, 10 amperes. Okay. And there is nothing but 30 by 3, 10 amperes. Okay. That is 30 by 3, 10 amperes. Okay. Then use this. If I substitute there, so this I of 0. So use this. That itself is I of 0. So use this in the main equation. That itself is a total equation. Now, if you use there, yes, this I of 0 is 10 is equal to e power 0, 1 into A1 plus A2 into 0. So A1 is 10. That is the first equation. Then what I want, di of 0 plus by dt. For di of 0 plus by dt, I need what? T equal to 0 plus circuit. Okay, na? I need what? T equal to 0 plus circuit. So I need what? T equal to 0 plus circuit. So now T equal to 0 plus circuit, if you go, first of all, switch got open. When switch got open, this 2 ohms is also waste. Then we know, yeah, initial condition, let us also find this also, sir. See, one more thing we require here is initial condition. This voltage also we require. What is this voltage? This voltage is current into resistance, that is 10 volts. Why? Because this is 10 volts, 10 amperes into 1, 10 volts. So with this information, 0 plus circuit. Now the switch got open here, capacitor short with initial voltage, and inductor open with initial current. Okay, inductor, capacitor short with initial voltage, and inductor open with initial current. Now I need what? To find di of 0, I need VL of 0 plus. So if you write a KVL, KVL minus 10, that is 30, because 10 3s are 30, plus another 10, 40, plus VL of 0 plus is 0. Okay, na? Because current source is already in series. Yes, current source is already in series. Please understand the concept here. Because current source is already in series, minus 10, plus 10 3s are 30, plus 10 1s are 10, plus VL of 0. So what is VL of 0 plus then? VL of 0 plus is minus 30. VL of 0 plus is minus 30. Okay, VL of 0 plus is minus 30. When VL of 0 plus is minus 30, then di of 0 plus by dt is VL of 0 plus by L. That is minus 30 by L. Now what is L? What is L? L is 1. L is 1. So this is minus 30 amperes per second. Now use this by differentiating the main equation. So first, if I do di of t by dt, if I do this di of t by dt, yes, if I differentiate uv dash, one is e power minus 2t. Okay, differentiation of this is a2t. That is, this is 0, this is a2. Okay, plus vu dash plus a1 plus a2t into, if you differentiate the exponential term, minus 2 e power minus 2t. Now put t equal to 0. Now if you put t equal to 0, this is how much? Minus 30 is equal to e power 0 1 into a2. Okay, plus e power 0 1. Yeah, t equal to 0 0 e power 0 1 minus 2a1 minus 2a1. So this is 1 into all these things. Okay, that is 1 into a1 minus 2a1. That is second equation. So this is the first equation. Yes, first equation we already got here. Second equation we got here. But already a1 is 10 now. But already a1 is 10. So if a1 is 10, okay, if you put a1 is 10, then a2 is minus 10. Okay, if a1 is 10, yes, since a1 is 10, this becomes minus 20, there plus 20 minus, that implies a2 is minus 10. A2 is minus 10. Shall we got both a1, a2, sir? Now final total response is this I of t is, okay, a1, a2, see a1 is 10, a2 is minus 10. So a1 is 10, a2 is minus 10. So directly 10 e power minus 2t. This is a1 plus a2t. Na? A1 is already 10. Na? A1 plus a2t. Or what we got? A1 plus a2t. This is 10. So 1 minus t. 1 minus t. it becomes 1 minus t for all t greater than or equal to 0. Okay, so this is clearly what? This is clearly what? Yes, you see, this is clearly going to be critically damped. This is clearly going to be critically damped. Okay, it starts at where? It starts at 10 amperes. Final value is 0. If you put t tends to infinity, final value is 0. So in a what? It starts at 10 and final value is 0, but it is going in which way? Critically damped way. Okay, that is the meaning, because it is off process now, critically damped way. Okay, so it starts at 10. Yes, it starts at 10. It reaches 0, but in a critically damped way. Critically damped. Okay, critically damped. But don't misunderstand, it is first order, it is second order. Okay, that is an interesting conclusion. Okay, everybody. So now, sir, I am going to category 6. Small but important. Category 6 called AC transients. Very, very small but important. Transients, AC transients. In that first, RL circuit. All mathematics are RL circuit. So now I'm taking sinusoidal excitation and teaching here. I'm taking what? Sinusoidal excitation. R and L. Okay, I'm closing switch at t equal to 0. This is R and L. This is Vm sine omega t. This is Vm sine omega t. Okay, now because it is AC transient and we know the total response I of t is forced response steady state plus natural response transient. Whatever I am writing, listen sir. But because it is AC transient, this is AC steady state. This is AC steady state and this is the transient part. Transient part which we already know, first order RL. Now I write this solution is of the form. This solution is of the form. This solution is of the form I of t equal to, in AC for RL circuit, if I use sinusoidal voltage, current is also sinusoidal. That is Vm by Z sine omega t minus 5 plus a e power minus t by tau. We already know na, because in AC RL circuit, if I use sinusoidal voltage, current is also sinusoidal. Current is also sinusoidal, that is Vm by Z, but current lags voltage by an impedance angle phi. Okay, current lags voltage by an impedance angle phi, and this is a e power minus t by tau. Okay, na, a e power minus t by tau. Okay, a e power minus t by tau. That is the meaning. Okay, now here we know some things. Here we know Z is root of R square plus XL square, omega L square. Phi is tan inverse omega L by R, and tau is L by R. So impedance angle and time constant. We know all these things. Okay, we know all these things because AC fundamentals. But the challenge is to find again in a initial condition. So at t equal to 0, however, we know I is 0 because inductor will not allow sudden change in current, because when switch was open, current was 0. Even when you close the switch, current is 0. So that is why at t equal to 0, current is 0. If you put here now, sir, this becomes 0 equal to Vm by Z, but that becomes sine of minus 5, because t is 0 na, and this becomes A. So that implies A equal to plus Vm by Z sine 5. So total response is, okay, so total response is, this is the final answer. That is I of t is equal to, okay, one is Vm by Z sine omega t minus 5. That is the steady state part. Now A we got na, that is Vm by Z sine 5 e power minus t by tau. This is the transient. This is for all t greater than or equal to 0. So this is AC transient. So mathematics is there, sir, nothing to worry. So after finding the initial condition here, we got the answer. Now I am giving extra question. If input excitation, yes, if input excitation is phase shifted as V equal to Vm sine omega t plus theta, then output response is also phase shifted, which is I of t is equal to same steady state part Vm by z sine of omega t plus theta minus phi plus a e power minus t by tau. Again, here we know z and all these things, but again at t equal to 0, current is 0. Yes, at t equal to current is 0. If you put here, so 0 equal to Vm by z, this becomes sine theta minus phi plus a. So a is minus of sine, so total response is, so total response is, this all mathematics, sir. This total response is, now if I substitute a here, there is I of t is equal to Vm by z. Okay, this is sine of omega t plus theta already given minus phi, but a how much we got? Minus Vm by z. So this is minus Vm by z sine theta minus phi e power minus t by tau. Okay, understand. Now what are the bits came? What are the bits? First of all, IS objective. In the above expression, okay, in the above expression, for what circuit condition? For what circuit condition? Yes, for what circuit condition? Current in the circuit is free from transient. For what circuit condition? The current in the circuit is free from transient. Okay, in the above expression, for what circuit condition the current in the circuit is free from transient. Now we know this is the steady state part, this is the transient part now. So solution, I am writing solution. So I will equate the transient part to 0. That is this Vm by z sine of theta minus phi into e power minus t by tau is the entire transient current. I will equate to 0. If I equate to 0, this and this you remove. Yes, you will get it as, yes, sine theta minus phi is 0, which is sine 0. That implies, yes, theta minus phi degrees is 0. So theta equal to 5. But for RL circuit, this RL circuit now, what is 5? That is theta equal to tan inverse omega L by R. Theta equal to tan inverse omega L by R. Tan inverse omega L by R. Tan inverse omega L by R. Theta equal to tan inverse omega L by R. Okay, theta is equal to tan inverse omega L by R. Okay, na? Chalo. Now I am going to gate bit. Again, I am asking in the above current expression, in the above okay, current expression. Okay, for what circuit condition? For what circuit condition the current, okay, for what circuit condition the DC offset, listen to this, the DC offset value of current is positive maximum, maximum. That is the bit that was given in GATE 2019. In the above current expression, for what circuit condition the DC offset value of the current is positive maximum. Now, sir, please understand. See, this is called DC offset value. Always remember, see, this is called DC offset value. This is called what, sir? DC offset value. DC offset in power system also we learn, na, sir? DC offset value. Now that should be positive maximum. Positive maximum means this entire thing should be -1. Na? We know sine theta minus phi range is from, yes, -1 to +1. Yes or no? -1 to +1. Okay. Yes. Then range I am talking. But if it has to be positive maximum, then theta minus phi should be -1 for positive maximum. Now the solution here is sine theta minus phi should be -1. That is sine -90. Okay, that is theta minus phi is -90. So theta equal to -90 plus phi. That implies theta equal to minus 90 plus tan inverse omega L by R. Tan inverse omega L by R. This is the answer. This is the answer. Tan inverse minus omega by R. Okay, that is a gate bit. See, this gate bit came, sir. Okay, IS bit and gate bit. Now I'm writing extra things like note 1. What is this note 1? If input excitation voltage is in cosine terms, then also express the output response current in cosine terms. Okay, if input excitation voltage is in cosine terms, then also express the output response current is in cosine terms. Okay, that is what, remember, sir. If cos is given, right cos, don't worry now. Now note 2. Okay, now in general in RL circuit in AC steady state, okay, that means already turned on, transient over, now talking steady state. Okay, I lags V by phi, which is the impedance angle. Yes or no? Yes, I lags V by impedance angle. So once it is turned on, this is AC voltage. I am talking RL circuit, sir. This is the AC voltage. And you know, current lags voltage by an impedance angle phi. Current lags voltage by an impedance angle phi. Current lags voltage by an impedance angle phi. Okay, this angle is called phase angle. Okay, this angle is phi. So yes, then these are natural zero current points. These are called natural zero current instances. These are natural zero current instances in time. Okay, so once see here, turning on process we explained, sir, but imagine that it is turned on, all this transient happen. Okay, and this response will come, but as t tends to infinity steady state, this becomes zero. Only steady state exists. That steady state AC we already studied now. So now that steady state, if it is reached already, yes, in general in RL circuit in AC steady state, current lags voltage by an impedance angle phi. Now, sir, now there is a chance that we can avoid transient while removing. Now these are natural zero current points now, sir, and that and current value itself is initial condition. If initial condition is there, transient will come, natural part will come. But if you can interrupt the circuit, interrupt means open. Yes, if you can interrupt the circuit exactly at these points where current is zero, we can avoid transient because there are natural zero currents points. So if we can interrupt the circuit exactly at these instances. Yes, if we can interrupt the circuit exactly at these instances where current is zero, we can completely avoid transient. We can completely avoid transient. So if we can interrupt the circuit exactly at these instances where current is zero, we can completely avoid transient. So the concept is here, interruption means breaking. Breaking means switch is opening. Interruption means breaking. Breaking means switch is opening. Okay. So at t equal to t0, if I open the circuit such that this current is naturally zero, then we can avoid a transient. Okay, that is the meaning here he is asking. Here breaking, sir, interruption means breaking. Interruption means, please understand, it is breaking, opening. Already it reached steady state. That is why your switch is opening. So if we can interrupt the circuit exactly at these instances where current is zero, we can completely avoid transient. So the condition is, so at omega t0 equal to phi. Yes, omega t0 equal to phi, because at what instances are with respect to zero crossover of voltage, this is phi. Again, with respect to zero crossover voltage, this is phi, phase angle. This is also phi, like that. So at omega t0 equal to phi, if we open the switch, if we open switch, okay, we can avoid transient. We can avoid transient current while opening, current while breaking, Don't confuse with this and this. Here what I told, for what circuit condition the current is free from transient, that is the condition. But here at what instant if you open the current, transient current is zero, because initial condition is zero, current will be in transient current will be zero. If initial condition is zero, transient current is zero, for that you should open switch at here. So automatically if you substitute there, okay, now solve T naught, we get the value, we get time, okay, time instant. Okay, so I will repeat everything. Quickly listen, I will repeat, sir. Just go through this. I will repeat everything now. AC transient is easy, sir. Don't think it is tough. As long as your mathematics is there, everything is easy. Yes, everyone see this is RL circuit, but supply is sinusoidal voltage. So I'm turning on. Okay, now total response is force plus natural. But because AC input, steady state is AC. So we know in RL circuit in chapter 5, when I give sinusoidal input, current is also sinusoidal, but current lags voltage by an impedance angle phi. So that is the expression. And transient part is A e power minus T by tau. Okay, transient part is A e power minus T by tau. Okay, so we get these things. Okay, now initial condition we got A. Now this is the total response. So this is the steady state part. This is the natural part. So in chapter 5 we were missing this natural part, sir. Now we are finding this. That is extra. Then if supply is already phase shifted to plus theta, then current is also correspondingly phase shifted, but it's still lagging voltage by an impedance angle phi. Then again you substitute initial condition. This concept will come. Now this is called DC offset value, and this is a transient, total transient part, but this is called DC offset value. Okay. Now the first IS bit is for what circuit condition the current is free from transient, equated theta equal to phi. And second bit, for what circuit condition the DC offset value is positive maximum. If DC offset value is positive maximum, then the sine theta minus phi should be minus 1. Minus 1 into minus plus 1, maximum will come. So I should equate to minus 1, then this is the condition. Then if input is cos, right answer in cos, current also. But already once it is reached steady state, we know current lags voltage by an impedance angle phi. Now when current is already lagging by voltage by phi, okay, there is natural zero. There are natural 0 points. So if you can interrupt the circuit exactly at this natural 0, we can completely avoid transient. Okay, now we can completely avoid transient. That is the concept. Okay, now yes. So at omega t not equal to phi, you open the switch. Okay, we open the switch. That is a T naught equal to phi by omega. That we should do. Okay, but however, if phi is what? Tan inverse omega L by R. Phi is tan inverse omega L by R. Now let us understand RC circuit. Now here the big change is the significance of state variable is lost. Now that is why here I will take current only as state variable. Why? Now unlike DC, this is AC input na sir. Listen carefully sir. Unlike DC, this is AC sinusoidal input. Now when I give sinusoidal in steady state, now we should not say capacitor is open or short. It is exhibiting reactance na sir. This is different now. See, if it was DC, we are always worried about the state conditions because in DC, inductor short, capacitor open like that. But in AC, no, when you are giving frequency, capacitor exhibits reactance. It is AC resistance. So now there is no confusion here. So I can take current itself as state variable, nothing wrong. So again, this current is steady state current plus transient current. Steady state current plus transient current. Okay. But again, we know AC steady state now, this solution is of the form. This solution is of the form. This solution is of the form. Okay, this solution is of the form. This I of t is equal to Vm by Z sine omega t plus phi plus a e power minus t by tau. Vm by Z sine omega t plus phi a e power minus, because current leads voltage. So here also we know that what is Z here? RC na sir. This is root of R square plus XC 1 by omega c square. Phi is tan inverse, yes, 1 by omega RC. Okay, tan inverse 1 by omega RC. And tau is however RC. Tau is however RC. Okay, now we know these things. Chalo, we know these things. Okay, we know these things. Okay, now again, we need initial condition, na sir. However, here also we know at t equal to 0, current is 0. Yes, if you substitute that, then if you put t equal to 0, current 0. So if you put this here, this is 0 is equal to Vm by Z sine plus phi, okay, plus A. So A is minus Vm by Z sine phi. DC offset value is negative here, sir. So total response is, total response is this I of t is steady state part. We know it is leading Vm by Z sine omega t plus phi minus Vm by Z sine phi e power minus t by tau. Okay, Vm by Z sine omega t plus phi. This DC offset is negative here for all t greater than or equal to 0. Now here also I am giving question. If input excitation voltage, okay, is phase shifted to, because such questions are asked, sir, is phase shifted to V equal to Vm sine omega t plus theta, V equal to Vm sine omega t plus theta, then output response is also phase shifted to, okay, now that I of t will be, now current will further lead na, that is Vm by Z sine omega t plus theta plus further leading plus a e power minus t by tau. Now again initial condition we know at t equal to 0, I is 0. If I put there, then if I put there 0 equal to Vm by Z sine theta plus phi, okay, plus a. So a is minus this. So total response is, that I of t is equal to Vm by Z sine of omega t plus theta plus phi. Okay. Now a how much we got? Minus Vm by Z sine of theta plus phi into e power minus t by tau. Chalo, this is the steady state part. This is the transient part for all t greater than or equal to 0. Now again question. For what circuit condition? Okay, I'm expecting such questions, sir. For what circuit condition? For what circuit condition? For what circuit condition? the current in the above circuit, the current in the okay, okay, for what circuit condition? In the current expression I will write. For what circuit condition? In the above current expression, in the above current expression, transient part is 0. Transient part is 0. I will ask like this. Okay. For what circuit condition in the above current expression, the transient part is 0. So solution, I will equate the transient part to 0. So this Vm by Z sine of theta plus phi has to be 0. Okay. Into e power minus t by 2. Okay. Into e power minus t by 2 has to be 0. If you equate to 0, okay, that implies yes, theta plus phi is okay, sine theta plus phi is sine 0, that is 0. So theta equal to minus phi, theta equal to minus phi. So theta equal to minus tan inverse 1 by omega r. That is the meaning. Theta equal to minus phi, minus tan inverse 1 by omega r. Okay. Okay, theta equal to minus phi. That is minus tan inverse 1 by omega r. Okay, so that is the first thing. Now I'm giving another question here. Everybody, I'm giving another question. In the above current expression, everybody listen, in the above current expression, for what condition, the DC offset value of current is positive maximum. Okay, in the above current expression, for what circuit condition the DC offset value is positive maximum? So the DC offset value, so we know this is the DC offset value of the current. Now this should be positive maximum. This should be positive. See, already minus is there, but this should be positive maximum, means sine theta plus phi should be minus 1, because minus 1 becomes plus now. Maximum value is however 1. So sine theta plus phi should be minus 1. So the solution is sine theta plus phi should be minus 1. That is sine minus 90. So theta plus phi is equal to minus 90. So theta equal to minus 90 minus 5. Minus 90 minus 5. But there is nothing but theta equal to minus 90 minus tan inverse 1 by omega RC, because it is RC now. So these bits I am expecting. Now another just note I am writing here. Another note. Yes, here also remember, if input excitation is in cosine terms, okay, cosine terms, then express the output response also in cosine terms. Okay, if input excitation is in cosine terms, then express the output response also in cosine terms. Okay, if input excitation is in cosine terms, then also express the output response in cosine terms. Okay na? Chalo, with this AC transient, whatever minimum I gave, that is enough for exam like GATE and IES, sir. Every bit I covered. So read this, are all mathematics only. See, however, this part you will learn in power system and power electronics. See, in power electronics, condition for finding beta, switching power electronics switch in transient state, all these things will come there. Okay, that part you have to be very, very careful. And I'm giving you the basics which are necessary for exam. Okay na? So now I'm going to the most powerful, but last but not the least, it is the most powerful category, 7th category. Okay, category 7, which is yes, circuit analysis in S domain. I call this as S domain. I will tell you why. Okay, or Laplace transform application to circuits. Laplace transform application to circuits. Okay, Laplace transform application to circuits. Okay, Laplace transform application to circuits. Okay, Laplace transform application to circuits, or I can say advanced circuit analysis. Advanced circuit analysis. So why we should use Laplace? See, so far we did only second order, and that to standard circuits. But now what is the advantage here? Chalo, what is the advantage? Yes, advantage is first higher order circuits. Yes, higher order circuits we can do. Higher order circuits. Then two, any type of input, okay, any type of input, not only DC and AC. I will give ramp, parabolic, anything. Higher order circuits, not only second order, third order, fourth order, fifth order, you can do any type of input you can give. Non-canonical forms, non-canonical forms, where neither pure series nor pure parallel, anything we can do. So when to use Laplace means, you remember, sir. So until now what I gave is almost 80-90% only. But when we will come Laplace only in this case, first of all, if circuit order is very high, then any special input is given, and also non-canonical forms I will use Laplace. So first here also equivalent circuit representation. Okay, equivalent circuit representation of passive elements in transient state. Okay, equivalent circuit representation of passive elements in transient state. Okay, equivalent circuit representation of passive elements in transient state. Equivalent circuit representation of passive elements in transient state in the first register. Okay, first I am taking register, but register is independent of frequency. Now, sir, we know it is R ohms only. Now you give any input like V of S in Laplace function, correspondingly I of S. So what is the Ohm's law now? So V of S is equal to I into R, I of S into R, or I of S is equal to V of S by R, V of S by R. Okay, now I'm going with inductor without initial condition. Okay, inductor with initial condition. Okay, inductor with initial condition. Okay, this is SL ohms. Okay, now this is V of S and this is I of S. Okay, so here also, yes, because inductor at any frequency for any signal is SL ohms. So here V equal to IR, SL into I of S, and I of S is, okay, V of S by SL. Okay, that is the meaning here. This is without initial condition, sir. Now I'm coming to third. Third, capacitor again without initial condition. Capacitor without initial condition. So this is 1 by CS ohms. We know now, sir. Okay, then here again for any input, this is V of S, Laplace representation, and this is I of S. Now again Ohm's law. Yes, here V equal to IR, that is I of S by CS, and I of S is equal to CS into V of S. V of S. Okay, that is I of S is equal to C of S into V of S. Okay, now sir, with initial condition, this is more important. Now I'm coming to fourth, inductor with initial condition. This is interesting. So first I'm taking the circuit here. Let us take, this is inductor and initial condition is also there. First I will show in time domain. This is V of t, I of t, any input it is. Not only DCAC, it can be any input. Now this, to satisfy KCL, this current has to represent in parallel only. Otherwise it is violation of KCL, na sir. See how can the initial current is equal to input current? Meaningless. Initial condition is from the previous state. This is input current from the next state. I cannot represent this I naught in series. If it is in series, this I of t and I naught should be same. How can the current from the previous state is equal to input current? So I have to compulsorily represent this in parallel only. Okay, this is V of t and this is I of t. Otherwise, it is violation of KCL. Now, I will represent in Laplace domain. Now, if I represent this in Laplace domain, this becomes V of s. This becomes I of s. This is SL ohms. And this becomes I naught by s. This become I naught by s. Now finally, if I write this, here with initial condition, yes. Now I'll do source transformation technique. Current source in parallel can be converted into voltage source in series. Current source in parallel with resistance can be converted into voltage source in series. This is for any excitation V of s. This is response I of s. This is however SL ohms. Now what is this? V equal to IR. If you take IR, this is Li naught volts. Okay, Li naught volts. Okay, but what is the direction? Current is going down, so plus is down, up. So this is finally the equivalent circuit representation of inductor with initial condition. Reasons are very important. All this explanation is to tell why this came. This last circuit only you have to remember. Now again from Ohm's law, here I can write this V equal to IR. SL I of s minus Li naught, and I is V by R. V of s by SL plus I naught by s. Okay, everything I get. This is inductor with initial condition. Look at this, everyone. I will explain again. Look at this. Okay, see, inductor with initial current. Previously, this is inductor without initial condition, sir. This is inductor with initial condition. Let us say inductor is already having current I naught, but I should represent in parallel only. Why? Because in series I of t and I should be equal. How can the current from the previous state is equal to present input current? Otherwise, it is violation of KCL. So I should show in parallel. Now current source in parallel can be converted to voltage source in series. First I went to Laplace. So V of t become V of s, I of t become I of s, L is SL. Now what is the Laplace transform of constant K by S? That is I naught become I naught by S. So current source in parallel become voltage source in series. Current is going down, so plus is down. Okay. Yes. So this is the equivalent circuit represent. So remember, sir, in inductor equivalent circuit with initial condition, the direction in which current entry is taken as minus Li naught and SL. Remember, sir, very, very important. Now I'm giving capacitor with initial condition. Okay. Now I'm giving capacitor with the initial condition. So let us consider, first a capacitor with initial voltage. This is our V of t. This is I of t. Now I should represent in parallel only. Otherwise, it is violation of KVL na. V of t, I of t, and this V naught I should show series only, sir. Let me correct. Why? Because see, this initial voltage is from the previous state, and I am giving V of t in the next state. If I represent in parallel, then V of t equal to V naught na. But how can the present input voltage is equal to previous voltage of any value? It is meaningless. Otherwise, it is violation of law of conservation of charge, or law of conservation of energy. KVL violation, na sir. I told you such things. Never we can connect two voltage sources of different values in parallel like that. So yes. So this V naught is from the previous state, and I'm giving V of t in the next state. If both are equal, then I can represent them in parallel. Otherwise, it is violation of KVL. So I should represent compulsory in series. I should represent compulsory in series. Okay, now I will represent in Laplace. Now if I represent in Laplace, yes, if I represent in Laplace, everybody, now if I represent in Laplace, this becomes V of S, this becomes I of S, this is V naught by S, 1 by CS ohms. One by CS ohms. Okay. One by CS ohms. V naught by S and 1 by CS ohms. Okay, now if I write a KVL, chalo, this V of S is, okay, I of S by CS plus V naught by S plus V naught by S. And also I of S is equal to CS V of S minus CV naught minus CV. So these are the things you have to remember. So this is finally, remember, capacitor with initial condition. So that is how, please remember this circuit, sir. Now see, I'm giving you a classical problem to understand really what is the meaning of this. Everyone plus listen now. Once you understand this now, sir, we can do any level problem, sir. Any level, I'm telling you, any level problem we can do. So this is the first problem I'm starting. If I of 0 is 10 amperes, find I of t for all t greater than or equal 0, A in time domain, B in S domain, that means in Laplace transform, in S domain also, in Laplace. See the difference. And this is the circuit I'm giving. Two ohms, 1 ohms, half Henry, and this is I, and this is I by 4, I by 4, I by 4. Yes, sir. See, first I will do in time domain. Everybody listen now. Yes, I will do first in time domain. Today I will do my best, sir. See, this question is the most dangerous. First day also you are asking, now also you ask. Today entire syllabus I am trying my best. If it is there also, we will take care. Don't worry. But see, sir, you tell me this, Vishnu, am I covering everything and so much content or not? You tell me, Vishnu. Tell me, Vishnu, yes or no? You tell me that first. So many problems, so many models, everything at one place. I am giving or not? Yes, you tell me first, Vishnu. Am I skipping anything? So many models, every topic, so many examples. Yes or no? You tell me, Vishnu. Yes or no? So that I will take care. If syllabus is there also, how to do? I know, no, sir. I will take care of it. Don't worry. One student, Bimalendra Sway, is saying, sir, it is already study state. How can we say we can avoid transient? Like one opening transient will come, na. Bimalendra Sway, you see, already it reached steady state, sir. When you are opening again, because of initial condition in energy, because energy can neither be created nor destroyed, when you turn off, surge will come. That we can avoid. There is a meaning here. Already once it reaches a steady state, I know turning on transient is over. But while turning off also transient will come. That we can avoid. So off process you have to think. In the last expression, steady state current is already there. But transient part means when you turn off that initial condition results into transient. That we can avoid. There is a meaning. And yes, as anonymous attendee told, these equations we get in fault analysis, subtransient, transient, and also in power electronics everywhere. And Vishnu, I cover everything now, sir. Vishnu, you please understand, I cover everything. Okay. Everything I'm covering. So take your time. Please take your time to learn, read again, and come. Okay. Yes, I will take care of it. Every content I'm giving, don't worry about it. Okay. Chalo. Now, sir, listen everyone. Now this question I'm asking. to find by time domain and Laplace domain. See the difference. See, first of all, this is step response or source free. There is no source, only dependent source. Now this is source free. Yes, this is source free. We know. Yes, this is source free because independent source is not there. Dependent source cannot work on its own, but it is working because of initial condition. So this is source free. Again, what is the order? First order. First order. And RL circuit. So what is the state variable? State variable is current through inductor. State variable is current through inductor. So this is source free first order RL circuit. Yes, it is a source free first order RL circuit and state variable is current through inductor. Now first let us do this in time domain. So in time domain, we know this current expression I of t is of the form I naught e power minus t by tau. I naught is already given 10 amperes. Given. This is already given. But the challenge is to find tau. Tau is L by R equivalent. Tau is L by R. So I want the equivalent resistance seen by the inductor while working. Now see this, sir. I want to know the equivalent resistance seen by the inductor while working. While working. So this is I. So automatically this is I by 4. Okay, I by 4. This is 2 ohms and this is 1 ohm. So I want the equivalent resistance seen by the inductor while working. Now this is Thevenin's category 1, 2 or 3. Thevenin's category 3. So Ohm's law. Let me inject a current of 1 ampere. Let me inject a current of 1 ampere and I will find V total like this. Chalo. Now if 1 ampere is I, this automatically become 1 by 4. Na? 1 by 4. Now out of 1 by 4 went. So this become 3 by 4. 3 by 4. Chalo. Now I am happily writing a KVL. Chalo, if you write a KVL, IR 3 by 4 into 2. Okay, plus IR plus 1 into 1 minus V total is 0. So I into R 3 by 4 into 2 plus 1 into 1 minus V total. So V total is 1 plus 3 by 2, 5 by 2 volt. Then what is R equivalent? R equivalent is V total by 1. Okay, that is 5 by 2 ohms. 5 by 2 ohms. Then what is tau? Tau is L by R equivalent. L by R. L is 1 by 2. R equivalent is 5 by 2. So this is 1 by 5th of a second. Now I of t is I naught. I naught already how much he gives her? 10. I naught e power minus t by tau. Minus t by tau. Tau is 1 by 5. Na? So I of t finally is 10 e power minus 5t for all t greater than or equal to 0. Okay, 10 e power minus 5t for all t greater than or equal to 0. Okay, this is already first category, sir. Source free first order RL circuit and state variable is inductor current. Okay, source free first order RL circuit and state variable is inductor current. We got this. Okay, now let us test it. Yes, let us test it in Laplace domain, S domain. Chalo, first to transform the circuit. I am transforming the time domain circuit into frequency domain circuit. Okay, I am transforming the time domain circuit into frequency domain circuit. Yes, understood. Chalo, now see, this time domain circuit I am transforming into frequency domain. First of all, registers are same. Okay, registers are same. Okay, this is however 2 ohm, this is 1 ohm. Now inductor with initial condition or without initial condition? Inductor with initial condition. Inductor with initial condition. So the direction which current enter is minus Li naught. Yes, minus Li naught. Minus Li naught and this is SL. Minus plus Li naught. L is how much? Half Henry. I naught is how much? 10. L is half Henry. I naught is 10. So total this become 5. And SL. S by 2 ohms. S by 2 ohms. Now I need the solution for what? I need the solution for this I of S. I of t become I of S. Now if this is I of S, this dependent source become I of S by 4. This dependent source become how much? I of S by 4. I of S by 4. Okay. So please understand. See this we understood here only, sir. See inductor with initial condition I told you na. The direction in which current enter minus Li naught SL. So here also you see the direction in which current enter minus Li naught. L is how much? Half. I naught is 10. So 5 volt SL. Okay. And if this is I of S, this become I of S by 4. Chalo, I need a solution for I of s. Okay, now KCL, KVL I will do. Now out of I of s by 4 went here. See, out of I of s by 4 went here. So this become 3 I of s by 4. This become 3 I of s by 4. Okay, out of I of s by 4 went here. So this become 3 I of s by 4. Now happily I will write a KVL. So KCL plus KVL. Now once you write, this become I into R. That become 3 by 2 I of s. Okay, plus another I of s minus 5 plus I of s into s by 2 equal to 0. So if I take I of s common, this is s by 2. 1 plus 3 by 2. Here 1 plus 3 by 2, 5 by 2. So 5 by 2 of I of s is equal to 5. I am taking right side. Okay, now if you observe, yes, this 2 if you take common, this I of s is 10 by s plus 5. Now I of t is inverse Laplace of I of s. So this I of t finally is 10. Yes, you see now inverse Laplace we know na sir. This I of s will become I of t, that is 10 e power minus 5t for all t greater than or equal to 0. Okay, same answer na. See, everybody same answer we got na. See, here also same answer. Here also same answer. Wonderful concept, sir. It's a wonderful concept. Okay, everybody see this now. See this problem. Then we can do any big problem now. Now I'll attack to do any big problem here. Okay, na? Same answer, na? Yes. Chalo, now I am asking the second question. Yes. Find V of t for all t greater than or equal to 0 using Laplace transform. Laplace transform method. Okay, na? Okay, find V of t for all t greater than or equal to 0 using Laplace transform. Everybody, find V of t for all t greater than or equal to 0 using Laplace transform. Chalo, now first we should build S domain circuit. First, let us check initial condition. Okay, na? So this is first of all, even though the switch is opening, one is going out. This is step response of second order. See, step response of second order series RLC. Why is step response? Even though the switch is opening, source is still available, na? So this is step response of second order. Okay, second order, step response of second order in series RLC. Now to write the S domain equivalent, first, yes, let us find the initial condition. Now, what are the initial conditions? Yes, I need the initial condition. One is this I of 0 minus, and one is this V of 0 minus. Okay, I need this V of 0 minus also. Okay, I of 0 minus and V of 0 minus. Now see, imagine switch is closed for DC, inductor short, capacitor open. Switch is closed in the previous steady state, inductor short, capacitor open. So what is the current now? 30 by 6. 30 by 6, this is 5 amperes. And what is the voltage? When 5 amperes is going through 1, this is 5 volts. When 5 amperes is going through 1, this is 5 volts. Okay, when 5 amperes is going through 1, this is 5 volts. Now with these basics, I can write the S domain circuit. Chalo, if I write the S domain circuit, everybody, yes, in S domain, watch this. Inductor with initial condition. Inductor with the initial condition. And this is capacitor with initial voltage. Capacitor with initial voltage. Inductor with initial condition and capacitor with initial voltage. Switch has opened, that 1 ohm is gone. So this become now Laplace now 30 volts become 30 by S volts. R is R. This is 5 ohms. This inductor with initial condition, the direction which current enter minus L I naught, minus plus L. L is how much? 1. I naught is 5. L I naught 5 volts. SL, this is S into 1 S ohms. And what about this? V naught by S. What is V naught? 5. Yes, V naught by S. 5 by S volts. 5 by S volts. And this is 1 by CS. 1 by CS. 1 by 4S. That is 4 by S ohms. Okay. 1 by CS. 4 by S ohms. And now total voltage across capacitor is yes. This total V of S. Okay, this is total voltage. Because voltage across capacitor is including its initial condition. Voltage across capacitor is including its initial condition, because this is total capacitor, not only this as capacitor. Where this 5 by S volts is coming, that is the initial condition only. Na? Chalo, now directly nodal analysis every day. Chalo, I am taking this itself as node voltage. Yes, now nodal equation. If I write the nodal equation, everybody see now. Yes, this is V of S, because we are solution for V of S now. V of S minus 30 by S minus 5 volts all by total impedance. What is impedance? Yes, S plus 5 ohms plus this is how much? V of S minus 5 by S whole by impedance, that is 4 by S equal to 0. Now if I simplify, first if I take V of S common, this is 1 by S plus 5, 1 by S plus 5, and this is S by 4 plus S by 4 is equal to, now this is 30 by S into S plus 5, 30 by S into S plus 5. Okay, 30 by S into S plus 5. Okay, and that is 5 by S plus 5, 5 by S plus 5, and the last part is 5 by 4 plus 5 by 4. So if I take this V of S, 4 into S plus 5, so this is now 4 plus S square plus 5S is equal to, here if you take LCM, 4S into S plus 5, this is 120 plus, if you take S plus 5, 20S plus 5S square plus 25S. Now you remove 4 and 4 and also this S plus 5, S plus 5. Then this V of S is equal to, that numerator becomes what? 5S square plus 45S plus 120 by S into, this is nothing but S square plus 5S plus 4 na? S plus 4 into S plus 1, it becomes S plus 4 into S plus 1. So this if I write, this is A by S plus B by S plus 4 plus C by S plus 1. A by S plus B by S plus 4 plus C by S plus 1. Okay, Laplace we are doing because I need a V of t na. Now here we know this how to find. Like first, A will become V of S into S when S is 0. So put V of S into S when S is 0. S is 0, 120. SS cancel, 120 by 4. 120 by 4 is how much? 30. B is V of S into S plus 4 when S is minus 4. So if you do that, S is minus 4 na sir, 16 5 is 80, minus 4 na minus 180 plus 120. S is minus 4 na sir, minus 4 into minus 3. So this becomes how much? 20 by 12. 20 by 12 is 5 by 3. 5 by 3. And now C. What is C? C, V of S into S plus 1 when S is minus 1. When S is minus 1. So if you put S is minus 1, that is 5 minus 45 plus 120. 5 minus 45 plus 120 all by S is minus 1. So this is minus 1 into minus 3. Minus 1 into plus 3. Okay, minus 1 into plus 3. So this will be how much now? Yes, minus 80 by 3. Minus 80 by 3. So now this V of S is, okay, this is A by S, that is 30 by s plus b by s plus 1 s plus 4, that is 5 by 3 into s plus 4. Okay, and this is c is minus 80 by 3 into s plus 1. Now finally v of t is inverse Laplace of v of s. That final answer is 30 plus 5 by 3 e power minus 40 minus 80 by 3 e power minus t for all t greater than or equal to 0. It is overdamped. Sir, the same problem today we did, sir, the biggest problem we did. Okay, the same problem. You see this. See, this network for r equal to 5 we did today. This network for r equal to 5 we did today. Okay, I will show you now. I will show you this network. I will show you now. Okay, today we did this big problem here. Yes, today we did this big problem. Yes, you see, sir, see this big problem what we did today in time domain. So in time domain, what happened? All this we have to find, sir. Omega naught, alpha, okay, under damped, over damped. First we have to declare. Once it is over damped, A1, A2, 0 minus circuit, 0 plus circuit, and initial conditions, all this came. So the same answer came now. You see 30 plus 5 by 3 power minus 40 minus 80 by 3 e power minus t. Now see this, sir. See this final here also. Same, na, sir. Ditto, na, sir. See the power of Laplace, everyone. See the power of Laplace. That 7-page or 8-page circuit become 3-page here. See here. That is the beauty of Laplace. That is the real beauty of Laplace. Okay. Tulasi, Srishta, and Satyanush, any doubt, or you can put down your hand. Tulasi, Srishta, and Tulasi, any doubt you can ask. Otherwise, put down your hand. It is disturbing me. Please put down your hand. Tulasi and Srishta. You are not there. I know. You are not in that. You just went and you are leaving now. So see the difference, sir. The same problem in Laplace, how it becomes. Chalo, now I am doing all the exam problems in Laplace. Yes, sir. Everybody, I am doing wonderful exam problems in Laplace. Get 2 marks. Chalo, everybody should do this now. Find I of t for all t greater than or equal to 0. This is given in exam. Get question. 2 marks. But now we can do such things in no time once we understood Laplace. So your switch is closing at t equal to 0. 20 volts, 2 ohms, 1 Henry, half farad. Chalo, I need the complete expression for I of t. Chalo, 1 minute, everybody do now. Yes, everybody. See, this is step response of second order series RLC, sir. Yes, step response of second order series RLC. In time domain, it will take 10 minutes, na, sir. In Laplace, I will do. Chalo, sir, that is faster. But check initial conditions here. No initial conditions. Yes, no initial conditions. Why? Because switch was open. Yes, when switch was open, yes, I of 0 minus is 0 and V of 0 minus is also 0. So, yes, no initial condition. So, directly I'm going to Laplace. So, if I directly go to Laplace, yes, directly without initial condition, 20 by S volts, 2 ohms, S ohms, 1 by CS, 2 by S ohms. Okay, and now I need the solution for I of S. Okay, I will solution for S. So KVL I am writing happily. So this is minus 20 by S plus I of S into 2 plus S plus 2 by S equal to 0. Here no initial condition. So I of S, if I take LCM S, S square plus 2S plus 2 is equal to 20 by S. So if you remove this, yes, this I of S is equal to, this is 20 by S square plus 2S plus 2. If I write this in standard form, 20 by S plus 1 whole square plus 1 square. Now I of t is inverse Laplace of I of S. Okay, that is nothing but 20 e power minus kt minus t sine t for all t greater than or equal to 0. So this is clearly underdamped, na, sir. See, e power exponential with sinusoidal means decayed oscillation, means it is underdamped. This is underdamped. Wonderful problem, sir. Underdamped. See how simple it came in 1 minute. 1 minute. If you do in time domain, it will take 10 minutes. Minimum 10 minutes. 0 minus circuit, 0 plus circuit, A1, A2 constants. All this will take a lot of time. So I'm giving another gate bit. Find V of t for all t greater than or is equal to 0. Okay, find V of t for all t greater than or equal to 0. Find V of t. So this current is 2 U of t amperes, half ohms, 1 Henry, 1 Farad. Okay, and I need this V of t. Shall everyone observe the question I am doing now? Observe the question, everybody. Everybody observe the question now. Okay, find V of t for all t greater than or equal to 0. Okay, na? So now in that regard, now this is also step response. This is also step response of second order. Why? Because suddenly 2 amperes is coming. Step response of second order. Current is given now. Okay. Now again, sir, doing in time domain is possible, but it is very lengthy and very, very tough and very, very difficult. Yes or no? And then in that case, what to do? Better you go to Laplace. But again, check initial condition. Here also no initial conditions. No initial conditions. Always check that. Luckily here again, no initial conditions. Okay. So really no initial conditions. I can neglect that. Okay. No initial conditions. So directly I'm going to S domain. Circuit. Why no initial condition? Because before 2 amperes is given, nothing is there. So directly in S domain, I'm writing no. Directly in S domain. So this is nothing but 2 by S amperes, half ohm, S ohms, 1 by S ohms. And I need the solution for V of S. So directly nodal analysis. This is V of S, nodal. So if I do nodal, yes, if I do nodal directly, yes, that is minus 2 by S plus V of S by half plus V of S by S plus V of S by 1 by S equal to 0. So if I take V of S common, S plus, okay, S plus 2 plus 1 by S is equal to 2 by S. Here again, if I take LCM S, S square plus 2S plus 1 is equal to 2 by S. So remove this. So V of S is directly 2 by s plus 1 whole square. Now this is already in standard form. Then v of t is inverse Laplace of v of s. S square na sir. So this is 2t, okay, e power minus t for all t greater than or equal to 0. So v of t is, so v of t is equal to 2t e power minus t. Okay, 2t e power minus t. Two t e power minus t. Okay, 2t e power minus t. Okay, 2t e power minus t. Okay, now yes. So it is a critically damped, clearly critical. Now I am going to IES conventional model. This is IES conventional. Find v of t for all t greater than or equal to 0. Now see the powerful features of Laplace now, sir. Everybody should see now this problem is something different. This problem is really different. 5 u of t amperes. So it is step current of 5 amperes. 1 ohm, 1 farad, 2 ohms, half Henry. And I need this expression for v of t. I need this expression for v of t. Okay, find v of t for all t greater than 0. Now this is step response second order, but it is non-canonical, sir. See this, sir. This is not pure parallel RLC. So those formulas of alpha 1 by 2 RC and omega naught we cannot directly use here. Understood, sir? There is a big change here. There is a biggest change. So this is second order non-canonical. Second order step response, but moreover it is non-canonical. That is very, very tough. Very, very tough. Non-canonical. That is very tough. But again, check initial conditions. No initial conditions. Here again, no initial conditions. Luckily, here also no initial conditions. Otherwise, we can write also. No initial conditions. So automatically, what we can do? Yes, because there is no initial conditions. Yes, because there is no initial conditions. Everybody. Yes, as there is no initial conditions, what I can do? Yes, here because initial conditions are not there, I am directly writing the S domain circuit. Okay, S domain circuit. So if you write the S domain circuit, okay, directly, this become 5 by S, 5 by S amperes, R is R, 1 ohm, C is 1 by CS, okay. Excuse me, schedule manager is calling, sir. Just give me 1 minute. Schedule manager is calling. Everybody, see, schedule manager also called me, sir. He is asking, sir, can you complete today? I told him, may or may not be, but anything we will arrange, sir. Don't worry. See, everybody, don't worry. But this part you listen 2 to 3 times, listen my notes, sir. We will happily have extra classes also. I will take extra things also. I will teach. But what all I want to give, see, sir, everyone, you tell me was first in question answer. Am I doing so many problems or not? You tell me, sir. You openly tell me. Am I doing so many problems or not? Everybody tell me, I am doing so many problems or not? Yes or no? So many, sir. See, you calculate 500, more than 500 bits I'm doing. You see, most of them are from the previous gate and previous IS only. So that is why it will save your time. So those who are all reasoning my notes multiple times, okay, you will have a lot of advantage, sir. That at least guarantee I will give you. Okay, that at least. Chalo, okay, let us come to this. Actually, schedule manager was asking whether I will complete today. I told I will tell you by 1 o'clock. If there is any change also, sir, tomorrow morning you will come to know. Don't worry. Okay. If there is any short of things, I will take extra, or Sunday I will take, or any other day when doubt session I will integrate there, like that. Don't worry. So now see here. Here this is step response, but non-canonical, sir, because this is neither series parallel RLC nor parallel RLC. So you cannot directly, yes, you cannot directly put the formula for alpha and omega naught. Yes or no? Yes, you cannot directly put the formula for alpha or omega naught. Okay, na? Chalo, now in that regard, yes, everybody, now in that regard, what I can do is, yes, now in that regard, I am directly converting into S domain. Okay, now in that regard, I will convert into S domain. So no initial condition, luckily, this is 1 by CS, 1 by CS, that is 1 by S ohms, 1 by S ohms. And this is, yes, this is R, SR, and this is also inductor SL ohms. No initial condition, luckily here also. Okay, so this is R 2 ohms and 1 by CS, 2 by S ohms. And I need the solution for what? V of S. I need the solution for V of S. Okay, I need the solution for V of S. So this is 5 by S, 1 ohm, 1 by CS, 2 ohms, and 1 by CS. Okay, na? So now I am writing nodal again. Everybody, I am writing directly nodal equation. So if I write the nodal equation, this is minus 5 by S plus V of S by 1 plus V of S by 1 by S plus V of S by 2 by 2 by S, 2 plus 2 by S. 2 plus 2 by S equal to 0. Equal to 0. So now in that regard, if I observe this V of S, so now in that regard, if you observe V of S, so this is automatically S plus 1, S plus 1, okay, plus, okay, S plus 1 plus S by, this is what, sir? 2, actually this is SL ohms. Let me correct it, sir. Please correct it. SL, na, this is not capacitor, SL. So capacitor is 1 farad, 1 by CS, but this is SL, S by 2 ohms, sir. Let me correct it. Yes, really sorry. One student told S by 2 ohms. So now this will become, yes, 2 by S plus 4. 2 by S plus 4 is equal to, that is 5 by S. 5 by S. So this V of S is, okay, if I take LCM, okay, let me take LCM first here. S plus 4. So this is S square plus 4S plus S plus 4 plus 2 is equal to 5 by S. V of S is S into S, 5 into S plus 4. Let me correct it. That is 5 into S plus 4. 5 into S plus 4 by, okay, this is S square plus 5S plus 6. S plus S into S plus 3 into S plus 2. S into S plus 3 into S plus 2. Okay, na? S plus 2. Now again Laplace, sir. This is A by S plus B by S plus 3 plus C by S plus 2. So what is A? A is V of S into S when S is 0. Okay, when S is 0, 20 by 6, 10 by 3. Then B is what? Okay, V of S into S plus 3 when S is minus 3. Okay, when S is minus 3, okay, this is 5 by, okay, minus 3 and minus 1. So 5 by 3. And finally, C is V of S into S plus 2 when S is minus 2. Chalo, when s is minus 2, this is 10 minus 2 and plus 1. So this is minus 5. So finally we get, okay, finally we get what we are getting. This v of s is equal to a by s. Okay, a is 10 by 3. Okay, 10 by 3s plus b by s plus 3. Okay, 5 by 3 into s plus 3 c minus 5 by s plus 2 minus 5 by s plus 2. Then v of t is inverse Laplace of v of s. So v of t is 10 by 3 minus plus 5 by 3 e power minus 3t minus 5 e power minus 2t for all t greater than or equal to 0. Okay, 10 by 3 plus 5 by 3 e power minus 3t minus 5 e power minus 2t. Okay, that is a wonderful problem, sir. Okay, so see, even non-canonical form we did. There is a beauty here. Okay, so now conclusion with 2 more models here, everybody. Conclusion with 2 more models. Okay, I will take a break, everybody. Take a break of 15 minutes. 12 o'clock we will meet again. Okay, then only 2 models to conclude and 2 ports I will start. Take a break of 15 minutes, sir, because I already fatigued. Take a break of 15 minutes, everybody. Yes, everybody, please come back. Are you there? Please raise your hand. Can you listen to me, please? Yes. Now see here. Now there are two more models to cover, sir. One is special input model. One is the ideal tank. Yesterday, one student was asking, sir, what about pure LC? I will tell that. So now this question is find VL of T. That means inductor voltage for all T greater than or equal to 0. For all T greater than or equal to 0. For all T greater than or equal to 0. If A bit Vs of T is 10 e power minus T, okay, volts for all T greater than or equal to 0, and B bit Vs of T is 3 delta of T. 3 delta of T. Okay. So I'm asking another interesting question here. Okay. Yes, I'm asking another interesting question on Laplace here. Everybody, this is for special function, special input function. Okay, or I will write here 10 e power minus T u of T volt. That is understood. U of T means it is starting from 0. And this is 3 delta of T volts. That means impulse voltage of 3 magnitude. And this is the circuit I'm giving. This is Vs of T, 5 ohms, half Henry, and this is VL of T. Shall everybody watch this question? Find the inductor voltage for all T greater than or equal to 0. Find the inductor voltage for all T greater than or equal to 0. Okay. Find inductor voltage for all T greater than or equal to 0. If Vs of T is 10 e power minus T u of T volts. Okay. And Vs of T is 3 delta of T volts. Okay. Sure. Now, sir. So here also there is no initial condition. Okay. Special input. Yes, this is special input problem. Special inputs. One is exponential spike and one is impulse. But again, no initial condition. No initial condition. So no initial condition. So whenever you see such special functions, neither it is pure DC nor pure AC, neither it is DC transient or AC transient. So immediately go to Laplace. So I'm writing the S domain circuit. Now here, what is the S domain? Again, no initial condition. So directly simple now, sir. This become Vs of S. This is R and this is SL ohms, S by 2 ohms. And now this is automatically VL of S. VL of S. So now voltage division rule for any function, voltage division rule. This voltage is total voltage into same by sum, same S by 2 by sum, 5 plus S by 2. So if you do this, VL of S is Vs of S into this is S by S plus 10, S by S plus 10. Okay, this is S by S plus 10. Okay, then now first A bit. Vs of T is how much he gave? 10 e power minus T u of T. Then what is Vs of S? Vs of is 10 by S plus 1. Then automatically what is VL of S? Convolution. This is 10 S by, okay, because in place of Vs of S, I am putting this 10 S by, okay, this is S plus 10 into S plus 1. Now Laplace, sir, this is A by S plus 10 plus B by S plus 1. So now directly I'm writing, see what is A automatically. If you observe A is how much here? See, if you observe A, VL of S into S plus 10 when S is minus 10. So this become minus 100 by minus 10, 100 by 9, 100 by 9. And what is B automatically? Put S is equal to minus 1. Okay, put S equal, that is minus 10 by 9, minus 10 by 9. So now I will say this VL of S is equal to, okay, 100 by 9 into S plus 10 minus 10 by 9 into S plus 1. Then VL of T is inverse Laplace of VL of S. So this VL of T is, okay, this is 100 by 9 e power minus 10t minus 10 by 9 e power minus t for all t greater than or equal to 0. That is the answer. See, sir, exponential spike is giving such function. Then B bit. BBT is another interesting. Vs of t is what? 3 delta of t. Okay, 3 delta of t. Then what is Vs of s? It is 3. Then what is VL of s? Convolute. Okay, if you multiply with 3, that is 3 into, okay, you are convoluting with this now. That is 3 into s by s plus 10. That is 3 into s by s plus 10. Now, if you write carefully, this s I will add and remove 10. By denominator is however s plus 10. That if you write properly, 3 into s plus 10 by s plus 10, 1 minus 10 by s plus 10. Now I wrote in standard form. Then VL of t is inverse Laplace of VL of s. That is nothing but 3 into delta of t minus 10 into e power minus 10 into, okay, e power minus 10t for all t greater than or equal to 0. Wonderful problem. Okay, these are the answers. So see, sir, another model I did for special function. So now onwards, any special function, any order, non-canonical, everything Laplace, sir. Now I'm going to special model again. This was a gate question, 2 marks. Find I of t for all t greater than or equal to 0. Find I of t for all t greater than or equal to 0. Switch is opening at t equal to 0. This is 10 volts, 5 ohms. This is 200 microfarad, half end. Okay, 200 microfarad, half end. And I need this current I of t. Okay, and I need this current I of t. Okay, 10 volts, switch is opening at t equal to 0. Switch is opening at t equal to 0. Okay, and this is half end. Okay, I of t for all t greater than or equal to 0. Okay, sir, you see, this is no doubt source free. Source free. Yes or no? SOURC, source free, because source is leaving. But second order. But the speciality here is ideal tank. Ideal tank circuit. Why pure LC na? Here R is not there. So that is why that formulas alpha, omega not here, more confusion it becomes. Okay. So pure LC. Now again check initial conditions. I want to check this V of 0 minus. And I want to check this I of 0 minus. So if switch was closed initially, inductor short, capacitor open. Now current through inductor is 10 by 5, 2 amperes. But when inductor is short circuit, voltage across inductor is 0. So please observe, sir, initial conditions now we are checking. See, in all the previous problems here, initial condition is not there. In other previous problem also, here initial condition is not there. Here also initial condition is not there. But here you check initial condition, it is there. When switch was closed in the previous steady state, 10 by 5, 2 amperes. And when inductor is short, voltage across inductor is 0. So that means inductor has initial condition, but capacitor does not have. So now with this, I'm writing the S-domain circuit. Chalo, S-domain circuit. So whenever you see such problems which are not definite in structure or topology, so it is a pure LC na, sir. R is not there. The confusions will come when you apply the formula. So it is called undamped. Okay. Damping ratio is 0. We study in controls like this, na, sir. Undamped. Damping ratio 0. Critically stable. So now in that case, now I am directly going to S-domain. Here capacitor is without any initial condition, but inductor with initial condition. So this is automatically 1 by CS, 1 by 200 micro S. Okay, this is minus Li naught. So minus L is half, I naught is 2. So minus 1 volt. And SL, S by 2 ohms. And I need the solution for I of S. Okay, now if you write a KVL, I of S into S by 2 plus 1 by 200 micro S is equal to 1. So if I take 2 common, S plus 10 to the power of 6 by 100 S equal to 2. Because 2 I took in the denominator and send it to the right side, 2. And this is S by 100 micro. Micro I will become up, it become mega by 100S. So this I of s again, further if I write this I of s is, okay, let me take here LCM first. Yes, this I will take it as s plus 10 to the power of 4 by s is equal to 2. So if I of s, if I take s square plus 10 to the power of 4 by s equal to 2. So I of s is 2s by s square plus 100 square, because 10 to the power of 4 I can write like 100 square. Now this is by s square plus omega square cos na. So I of t is inverse Laplace of I of s. So the final answer is C's are undamped sinusoid 2 cos omega t. Omega is 100t for all t greater than or equal to 0. So never ending oscillations. It is called undamped. Never ending. So with this are complete. Yes, with this I confirm complete transient analysis is over. All the 7 categories you read. First understand the problem in which category it will come, and it is turn on or turn off process. Turn on process means even steady state. Turn off process means yes, only transient part. And if circuits are non-canonical, go to Laplace. If circuits are higher order, go to Laplace. Double inductor, double capacitors, everything you can do now. Okay, and when teaching inductor capacitor also, the double inductor double capacitor, the proof you can understand. Okay, and all such special circuit like TAN circuit, special input functions, non-canonical, higher order, go Laplace. So this area you practice more and more. Yes, I will share my notes there. You can find such problems. Okay, so now with this we are into the last and official chapter here. We are into the last official chapter as far as syllabus is concerned. Okay, as far as syllabus is concerned, we are into the last official chapter, that is two-port networks. Okay, chalo sir, two-port networks. Sir, what I will do tomorrow, you will get the schedule tomorrow. Today by evening you will get it. Okay, if anything necessary, I will take up tomorrow also, or I will take up directly after 10 days in the doubt session only. I will take that extra topic. So don't worry. But today, strong introduction to two ports I want to give. Okay. Yes, I want to give very, very strong introduction to two ports. And again, it is a lot of mathematical and definitions. So please observe and follow carefully. Chalo sir, two port networks. What is this? It consists of, okay, two pairs of terminals, okay, two pairs of terminals describing the network, where the positive reference voltage polarities, and the positive reference okay, positive reference current directions are shown as below. That means this is my definition of two-port network. So what is two-port network? That is the meaning I am telling here. What is the meaning of two-port network? It consists of two pairs of terminals describing the network. Okay, there are so many applications in electrical engineering where we can model in two ports. That is why we are learning this chapter. So it consists of two pairs of terminals. This 1 dash is first pair, 2 dash is second pair. It consists of two pairs of terminals describing the network where the positive voltage reference polarity is this is V1, this is V2, this is positive voltage reference polarities and positive directions of currents. This is I1 and this is I2. So this is the definition, sir. So what is the meaning of two port? It consists of two pairs of terminals describing the network where the positive reference voltage polarities and the positive reference current directions are shown as below. Okay, positive reference voltage polarities and positive reference current directions are shown as below. Okay, that is the meaning. So if you want to define any two-port network, these are the references: positive direction for voltages and positive direction for currents. Okay, now then here out of the four parameters, okay, here out of the four parameters, okay, like V1, V2, I1 and I2. Okay, here we have four parameters now: V1, V2, I1 and I2. Here out of four parameters V1, V2, I1, I2, two of them are considered, okay, considered as dependent, and the other two, okay, other two as independent. Okay, here out of the four parameters V1, V2, I1, I2, two of them are considered as dependent and the other two as independent. other two as independent. So we have 4C2, that is 6 types. Yes, 6 types of parameters. 6 types of parameters with which we can define the two-port network. Okay, so here out of the 4 parameters like V1, V2, I1 and I2, okay, 2 of them are considered as dependent. Okay, any two of them are considered as dependent and the other 2 as independent. So we have total how many? Okay, out of 4, 2 are dependent. So out of 4, 2 are dependent. So we have 4C2. Okay, 4C2, that is 6 types of parameters with which we can define the two-port network. Okay, they are Y parameters, H parameters, ABCD parameters. These are the only there in syllabus. But still, G parameters and inverse ABCD parameters we will only learn, but this is not in the syllabus. Not included in syllabus. Okay, why? Because there is no applications. That is why in so many books like Sham series, other books, sir, there is no example also given. In Hayton, Kemerly, etc., there is not given. What is the reason not given? What is the reason not given? The reason they are not given because no applications. Okay, no applications. Okay, na? So that is the meaning. So out of the 4 parameters, 2 we take as dependent, other 2 as independent. So we have 4C2. That is total 6 types of parameters with which we can define the two-port network. Okay, na? That is the meaning here. That is the real meaning here. Then what are the rules here? What are the rules? The network inside the ports. The network inside the ports, okay, must consist of linear, passive, bilateral elements only. Okay, the network inside the port consists of linear, passive, bilateral elements only. Okay, linear, passive, bilateral elements only. Okay, the network inside the ports must consist of linear, passive, bilateral elements only. Then the network inside may also have energy storage elements. Okay, the network inside may also have energy storage elements L and C, but their initial conditions must be zero. But their initial conditions must be zero. Okay, but their initial conditions must be zero. That is the important thing. The network inside may also have energy storage elements L and C, but their initial conditions must be zero. Then the network inside, okay, the network inside may also have dependent sources. Okay, dependent sources. Okay, the network inside may also have dependent sources, but never an independent source in it. Okay, the network inside may also have dependent sources, but never an independent source in it. So these are the rules. Everyone read again. So everybody, what are the rules? See, what are the rules here? It is saying the network inside the box. Okay, the network inside the box must consist of only linear passive bilateral elements. Yes, that is the first thing. It may also have energy storage elements L and C, but their initial conditions must be 0. And also the third point, that it may have dependent sources, but never an independent source. It may have dependent sources, but never independent. Only such networks can be modeled. That is the meaning here. The meaning of this points is, only such models can be modeled in two-port networks. No, sir. Once to way, this anonymous attendee, who is this anonymous attendee? Raise your hand. Anonymous attendee, please raise your hand here. Shrestha, you are anonymous attendee. So this anonymous attendee, raise your hand. Okay. I told I am having class in the afternoon. You decide everything. That is why your name you never enclose, na sir. You have the power to give directions to teacher. So I don't want to respond to you. Chalo everybody. Yeah. I will plan, sir. Don't worry. I will plan. Schedule manager also. I told I will confirm after 1 o'clock. Don't worry. I will take my responsibility to complete the syllabus. Don't worry. Others don't worry. Okay, na? Okay. It is my responsibility to complete. So now see here. Yes. And the network inside the ports must consist of these things, sir. These are the rules. That means everything in the world cannot be modeled in two ports. Everything in the world cannot be modeled in two ports. Only such networks can be modeled in two ports. Okay. Then what is symmetry in two-port networks? Okay. What is symmetry? Listen to this, sir. What is symmetry in two-port networks? In two-port networks. What is the meaning of symmetry? We already learned symmetry in one-port network. Mirror image like that. In two ports also is asking. Okay. What is the meaning of symmetry in two-port networks also is asking. Okay. Let us understand what is asking. Symmetry in two-port networks also. Let us answer now. Okay, now the definition original for symmetry. Yes, the original definition for symmetry is like this, sir. Everybody, the original definition is, yes, it is something like this. If the ratio of excitation to response, at both the ports are independently equal. Okay, if the ratio of excitation to response at both the ports are independently equal with respect to defined network conditions, such as open circuit or short circuit or terminal impedance, etc. Terminal impedance, etc. is said to be symmetrical. Okay. If the ratio of excitation to response at both the ports are independently equal. Yes, if the ratio of excitation to response at both the ports are independently equal with respect to the defined network conditions such as open circuit or short circuit or terminal impedance, etc., then it is said to be symmetrical. Okay. Now, what is the meaning? I am writing the meaning here. Suppose the same network I am taking here, the same two-port network I am taking here. Okay. This is 1, 1 dash, 2, 2 dash. Again, I am taking here the same two-port network, Here also I am taking 1, 1 dash, 2, 2 dash. Okay. 1, 1 dash, 2, 2 dash. Now see, if the ratio of excitation to response. So here you see, suppose I give voltage V1, which is allowing current I1. Excitation is voltage, response is current, and I am taking open circuit definition. Here also I am taking voltage V2, which is allowing current I2, and I am taking same condition, open circuit. Suppose if I take open circuit, take open circuit. If I take short circuit, take short circuit here. If I take open circuit, take open circuit. Short circuit, short circuit. Terminal impedance. Suppose I put 1 ohm here, put 1 ohm here. Put 10 ohm here, 10 ohm here, like that. So if the ratio of excitation to response at both the ports, here excitation is voltage, response is current. Here also excitation is voltage V2, response current I2. If the ratio of excitation to response at both the ports are independently equal with respect to the defined network condition. Here, what condition we took, for example, open circuit. Any condition we can take. Now I will say the network is symmetrical. The network is symmetrical. If yes, V1 by I1 is equal to V2 by I2. That is the meaning. Okay, the network is said to be symmetrical. But I'm writing a note. However, for simple passive bilateral networks, symmetry can be identified as mirror image. Yes, mirror image property with respect to port. So if network is there, okay, like this, okay, like 1 dash 2 dash, okay. Now if this is mirror image, see, with respect to center line, if this is mirror image here, mirror, this and this are mirrors, okay, okay, then also we can say it is symmetrical. So symmetry is a mirror image property, okay. If the ratio, see, original definition is this, sir. Read this original definition, everybody. Okay, if the ratio of excitation to response at both the ports are independently equal, okay, here like V1 by I1, there V2 by I2. If the ratio of excitation to response at both the ports are independently equal with respect to the defined network condition is said to be symmetrical. Okay, now here that is the meaning. I took open circuit condition and V1 by I1 equal to V2 by I2. But mirror image also symmetrical. So with respect to this axis which I wrote, if that side port and this side port would look looking exactly identical, then it is mirror image. That is symmetrical also. That is also symmetrical. Then reciprocity in two-port networks. Reciprocity in two-port networks. Okay, what is reciprocity in two-port networks? Okay, here again, if two-port network obey, reciprocity theorem, okay, then it is reciprocal. If the two-port network obeys reciprocity theorem, see, reciprocity theorem we already wrote now. The ratio of response to excitation remains constant if the positions of source and load are interchanged. That is different. Here, ratio of response to excitation at both the ports independently equal, that is symmetry. But here, ratio of response to excitation remains constant even if the positions of source and load are interchanged. Okay, that is different. So if the two-port network obey reciprocity theorem, then it is reciprocal. This theorem statement I gave in reciprocity long back, yes or no? But however, any linear passive bilateral network, any linear passive bilateral network is always reciprocal. Okay, since reciprocity means passivity. Reciprocity means passivity. Remember that. Okay, now if network is passive means it is 100% reciprocal. Chalo, first let us define them. First, Z parameters. What are Z parameters called as? Z parameters are called as open circuit impedance parameters. Okay, Z parameters are called open circuit impedance parameters. Okay, na? Yes, open circuit impedance. That means under open circuit condition we are finding the impedance. Here what is that? V1, V2 are dependent. Yes, dependent. But I1, I2 are independent. V1, V2 are dependent, I1, I2 are independent. Then automatically V1 is Z11 I1 plus Z12 I2, and V2 is Z21 I1 plus Z22 I2. Okay, Z21 I1 plus Z22 I2. Now symmetry condition. What is the condition for symmetry? All these formulas you remember, sir. Z11 equal to Z22. Okay, Z11 equal to Z22. And what is the reciprocity condition? Yes, reciprocity condition is Z12 equal to Z21. Z12 equal to Z2. Okay, then second Y parameters, which are also called short circuit admittance parameters. So what is the meaning? That means under short circuit condition, either port 1, port 2, we have to find this. Here again, what is the definition here? I1, I2 are dependent. Yes, I1, I2 are dependent, and V1, V2 are independent. V1, V2 are independent. Then what is the equation? I1 is Y11 V1 plus Y12 V2. I2 is Y21 V1 plus Y22 V2. Y22 V2. Now condition for symmetry. Y11 equal to Y22. Y11 equal to Y22. And condition for reciprocity. Is Y12 equal to Y2. Y12 equal to Y2. Okay, Y12 equal to Y2. Okay, now I'm coming to third. H parameters that are hybrid circuit parameters. Yes. H parameters are hybrid circuit parameters. Here, input voltage, output current are dependent. Yes, input voltage, output current are dependent. But input current and output voltage are independent. That is how you have to remember. Then what are the equations? V1 is H11 I1 plus H12 V2, and I2 is H21 I1 plus H22 V2. Now condition for symmetry. Here condition for symmetry is H11 H22 minus H12 H21 whole equal to 1. And condition for reciprocity. Yes, condition for reciprocity is H12 is equal to minus H21. H12 is minus H21. Then if you go to fourth. Okay. Okay, just for note, I will write G. Okay, though G parameters are not there, I will write inverse hybrid. G parameters are called inverse hybrid. Parameters. Okay, inverse hybrid parameters. Directly, I am writing the equations are just remember here ulta. I1, V2 are dependent and V1, I2 are independent. So I1, V2 are independent. So G11 V1 plus G12 I2. Here G21 V1 and G22 I2. Okay. Here symmetry is G11 G22 minus G12 G21 whole product is equal to 1. Reciprocity is G12 equal to minus G21. Okay, but it is not there in the syllabus because no applications. Now I'm coming to the fourth one. These are called ABCD parameters or transmission line parameters or transmission circuit parameters. These are all definitions, sir. Transmission circuit parameters. Here, input voltage, input current are dependent. Yes, input voltage, input current are dependent. But output voltage and output current are independent. Then the equation is V1 is AV2 plus BI2. I1 is CV2 plus DI2. Condition for symmetry, A equal to D. Condition for reciprocity, AD minus BC equal to 1. condition for symmetry A equal to D and condition for reciprocity is AD. But here I want to write a note. Only in ABCD parameters, yes, only in ABCD parameters. Now the positive reference direction for I2 is something different, please. So in ABCD parameters alone, the positive direction for current I2 is leaving the port. This is positive direction. Positive direction. That you remember. So, because in transmission, we have to transmit, sir, either signal or power, we need to transmit. But transmit means this current I2 should leave this box. Then only it is called transmission. So the positive direction for current I2 in ABCD is leaving the box. But as per our original definition, original definition wise, entering the box is positive. But here, leaving the box is positive. But if you still take, but here if you still take I2 entering, if you still take I2 entering, then you put minus here and do. Okay, that is the meaning here. That you remember. Okay, condition for symmetry and reciprocity. Now here also just for, just I will write inverse ABCD. Okay, inverse ABCD, just formulas. They are called inverse transmission. Inverse transmission circuit parameters. Circuit parameters. Okay, so if they are inverse transmission circuit parameters, just here ulta sir, V2 I2 are dependent, V1 I1 are independent. So V2 I2 are dependent. A dash V1 plus B dash I1, C dash V1 plus D dash I1. Symmetry again here, A dash equal to D dash. Okay, and reciprocity A dash D dash minus B dash C dash equal to 1. Equal to 1. Equal to 1. Okay, that you remember, sir. Not necessary, but this is not there in the syllabus. Okay, so first I gave only introduction. Okay, what is two port? Now, why we are learning, etc. I will tell you, sir. You have to wait, sir. Why we are learning? What is the reason? Okay, all this I will tell you. Wait, sir. You have to wait. Okay, sir. What is the reason we are doing, etc. I will tell you. Please wait. Until then, yes. Now see. Now this chapter has a unique application. Like example, you tell me. See where we are using two-port networks already. Yes, we are using in power system. Without two-port network model power system analysis, there Z bus or Z parameters are. See, in power systems, please understand, in power systems, first of all we use ABCD parameters by default. Yes or no? In power system transmission line modeling. Yes or no? Transformer model, transmission line model, generator model, ABCD is compulsory na? There we use. Also remember in power system, our Z bus in power system is nothing but Z parameters. But that is for more buses. Here I am taking two-port networks, means only two buses. There, any number of buses. And even Y bus is our Y parameters. Like that, sir. So where we are using two-port networks, means this is the best application. And also we use in transistor. See, in transistor circuits, in transistor BJT circuits, we use H parameters. We use what? H parameters. We use H parameters. In transistor BJT circuits, we use what? H parameters. That is hybrid circuit parameters we use. Okay, what we use? We use hybrid circuit parameters. Okay, we pakka use hybrid circuit parameters. So, what are the applications we are talking here? So, what is that we are getting? Yes, we are getting what? We are getting what here? So, applications like power system, we use default ABCD parameters. Z parameters are Z bus, Y parameters are Y bus, transistor. So, that is the application. Okay, so first in few minutes I am going to close, but I will give first definition based problems. So, first question: find Z parameters for the network below. One dash, two dash. This is 1 ohm, 2 ohm, 3 ohm. 1 dash, 2 dash. And this is 1 ohm, 2 ohm, 3 ohm. Okay. 1 dash 2 2 dash 1 ohm 2 ohm 3 ohm. I need Z parameters. See, whenever you see, now there is a shortcut for Z parameter. There is a shortcut whenever there is a T model, whenever there is a T model and impedance form, all are impedances. Okay, when T model impedance are there, then there is a shortcut for Z. What is the shortcut? I'm directly writing Z parameters are, now watch this, sir. Z parameters, see, Z11 is 1 plus 2, Z11 is 1 plus 2, 3 ohms. Z22 is 2 plus 3, Z22 is 2 plus 3, 5 ohms. And Z12, okay, Z22 is 2 plus 3, okay, there is nothing but 5 ohms. Now Z12 equal to Z21 equal to Z21 is 2 ohms, 2 ohms. Okay, na, that is important, sir. Everybody please observe. So first of all, what I want to say is, yes, everybody, yes, Z11 is 1 plus 2 3, Z22 is 2 plus 3 5, but Z12 equal to Z21 2 ohms. Now check it. I'm also checking by definition. Okay, check by definition. If I check by definition, now what is the condition to find Z11 and Z21? Okay, first I will write the equations. Now what are the equations? V1 is Z11 I1 plus Z12 I2, and V2 is Z21 I1 plus Z22 I2. Okay, now what is the condition to find Z11 and Z21? To find Z11 and Z21, here I2 should be 0. That is the meaning. To find Z11 and Z21, yes, to find Z11 and Z21, what should be 0? I2 should be 0. Okay, I2 should be 0. So if I put that condition here, watch this please. To the same network, I2 0 means what? Open circuit port 2. Yes or no? This is 1 ohm, this is 2 ohm, this is 3 ohm. Now I2 0 means this V1 is there, I1 is there, V2 is there, but I2 is not there. I2 is not there means no current is flowing in port 2. Open circuit port 2. When open circuit is there, no current can flow here because it is called open circuit impedance parameters. I2 0 means open circuit port 2, no current here. So this total I1, let me correct it. This total I1 only will flow here. This total I1 only will flow here. Understood? I am repeating, sir. See, shortcut first you remember. When it is a T model and impedance form, Z11 is 1 plus 2 3, Z22 is 2 plus 3 5, but Z12 equal to Z21 is 2 ohms. How to check by definition? Now from the equations, V1 is Z11 I1 and Z12 I2, and V2 is Z21 I1 and Z22 I2. The condition to find Z11 and Z21 is what? I2 0. Okay, na? Chalo, when I2 is 0, everybody, when I2 is 0, open circuit port 2. So I1 only will flow here. Na? Yes, I1 only will flow here. When I2 is 0, only I1 will flow here. Yes or no? Now, if I write the first KVL, V1 is 3I1. So automatically Z11 is V1 by I1. How much it is? 3 ohms. 3 ohms. Yes or no? KVL I wrote, sir. See, KVL I wrote. V1 is 3I1. Z11 is V1 by I1, 3 ohms. Yes, it is 3 ohms. Similarly, if I write the KVL here there is no voltage. If I write KVL here, directly V2 equal to 2I1. So automatically Z21 is how much? V2 by I1, which is 2 ohms. 2 ohms, which is 2 ohms. So similarly, to find Z22 and Z12, what you do, sir? Take I1 0, you'll get the answer. Okay, just checking, sir. Just checking for confidence. Okay, just checking. Nothing great here. Just checking. Now I'm giving the IES objective. See, IES objective on this concept. Okay, find Z parameters for this network. Okay, find Z parameters for this network. This is a filter application, sir. First, I want this Z parameters. So this is 1 Henry, 1 Farad, 1 Henry. This is 1 1 dash. This is 2 2 dash. Okay, 1 1 dash and 2 2 dash. Okay, now listen here. See, we know there is a shortcut if the network is in T model impedance form. Now, Z parameters for what impedance? Z parameters are called open circuit impedance. But here, impedance at what frequency? Any frequency. So here we should find impedance at any frequency. Any frequency. Any frequency means network function model. Network function model means S domain. Yes, this network can work for DC input or AC input, ramp input, triangular, sawtooth, anything, sir. So that is why now, see, previous problem is only resistor, no confusion. But this problem is pure inductor capacitor. So we are finding impedance. Impedance at what frequency? Any frequency. Any frequency we should model, and for any input, that means in S domain. Now, if I convert this into S domain, yes, if I convert this into S domain, now what happens, sir? This, yes, becomes Laplace domain. Laplace domain. Okay. So this becomes how much? S ohms. This is 1 by S ohms, and this is also 1 by S ohms. But we know there is a shortcut for T model. There is a shortcut for T model, but this is a pi model. Now, how to convert this pi into T? How to convert this pi into T? Convert delta to star transformation. If I can convert this delta to star, I will get the T model. So what this value will be? This value will be this into this 1 by S square by sum. Sum is S plus 2 by S. So overall, if you see 1 by S into S square plus 2. Similarly, what about this now? What about this part? This part will be this into this 1 by sum. S plus 2 by S. So that is S by S square plus 2. So this also will be S by S square plus 2. So now if you convert, yes, now if you convert into T model, yes, please now listen. Now if you convert this into T model, yes, after converting this into T model, now we are getting the answer, sir. T model impedance form, shortcut is there, where this value is how much now? This branch is how much? Yes, 1 by S into S square plus 2. Okay, these two branches are how much? S by S square plus 2. S by S square plus 2. This is also S by S square plus 2. Now the Z parameters are, this will be this plus this. Okay, that is S square plus 1 by S into S square plus 2. S square plus 1 by S into S square plus 2. This is 1 by S into S square plus 2. 1 by S into S square plus 2. Okay, that is the meaning. That is the meaning. Okay, that is the meaning. This is the answer. These are the impedance parameters at any frequency for any signal. That is the meaning of this mathematical modeling, sir. So last problem of the day, everybody, last problem of the day, gate question 2 marks, gate question 2 marks. Find Z parameters for this network. One dash, two dash. This is 1 ohm, 2 ohm. This is I1. This is plus and minus 3 I1. Sir, in this problem, there is no shortcut. See, in the first problem, this is impedance form T model, shortcut is there, and I also checked it. Here also all are impedances, and in T network, I converted from delta to star, then I got shortcut. but here you cannot do because there is a dependent source. Yes or no? Here you cannot do, there is a dependent source. Sir, I will first convert this into current source. See, let me correct it, sir. In the gate question, yes, let me correct it. Yes, it is now 3I1. See, let me correct it, sir. Everybody, this is a dependent current source because transistor model he gave. Later, we will do even dependent voltage source. That is more easy, in fact. So first, I am taking dependent current source. Yes, sir. In the gate model, please correct this. This is a current source. Everybody remember, in gate model, this is a current source. Okay, na? Yes, sir. Now I want Z parameters. Everybody correct this part. This is a current dependent current source because it is a transistor model he gave. But I want what? I want the Z parameters. So here there is no shortcut like P model impedance form, sir. There is no shortcut like this. Okay. Now, sir, here as per the definition, you know, the condition to find Z11 and Z21 is what? I2 should be 0. Chalo, let us put that condition here. Chalo, if I put that I2 0, everybody watch this. Okay, everybody watches. I'm making this I2 0. Okay, everybody watches. I'm making this I2 0. Okay, this is 1 ohm, this is 2 ohm. Okay, however, this is 3I1 and this is already I1. So now V1 is there, I1, and V2 is there, but I2 is not there. Okay, I2 is not there. I2 is not there. But see common sense. Now at this junction, if you apply KCL, this is I1, this is 3I1. This is I1, this is 3I1. So this has to be 2I1. But in a passive element, if this is positive, actually current should enter down. In a passive element, if this is positive, current should enter positive, but it is coming ulta. So here V1 is minus 2I1 into 1. So automatically Z11 is V1 by I1, which is minus 2 ohms, negative impedance, active network it is. It is an amplifier. Now, sir, taking I1, giving 3I1 means amplifier. Then second what I will do, everybody watch this. I will write a big KVL here because I need Z21 na, V2I1 na. So if you write a KVL, what is a KVL if you write? Yes, minus V1 or directly V2 I should na. Okay, starting from here. Minus 2I1 into 1 plus this is 3I1 into this current is same now because I2 is 0. This current is 3I1 only. 3I1 into 2, yes, 6I1 plus V2 equal to 0. So V2 is, yes, minus 8I1. That implies Z21 is V2 by I1, which is minus 8 ohms. This is minus 8 ohms. See here, there is no shortcut as there is a dependent source. Here, there is no shortcut as there is no dependent source. So I applied the definition. The condition to find Z11 and Z21 is what? I2 should be 0. So I2 0, remaining V1 I1 and V2 I2. Then I did KCL here. If this is I1, this is 3I1, this has to be 2I1. Then Ohm's law. But in a passive element, current should enter positive, but it is ulta. So V1 is minus 2I1. So Z11 is minus 2. And if you write a KVL, V2 is minus 811, Z21 is minus 8. Now, second condition. See, what is the condition to find Z22 and Z12? We got Z11 and Z21. Now, Z22 and Z12 condition is I1 should be 0. Now, listen, sir. If you make I1 0 in the question, if you make I1 0, dependent current source also becomes 0. Na? I1 0, dependent current source also 0. Dependent current source 0 can be replaced by open circuit. So, this will become something like this. Okay. Yes, I make I1 0. So, this I1 is 0. Then automatically dependent current source 0. I open it. So, this is 1 ohm. This is over 2. Okay. Yes, now automatically this is V1, but I1 is 0. This is V2, but this time I2 is there. But because I1 is 0, dependent current source 0, I open it. So same I2 also will flow here. Now KVL here. KVL V1 is 1 into I2. Okay. So automatically Z12 is 1 ohm. Z12 is same now, V1 by I2. There is nothing but V1 by I2. Okay, V1 by I2, which is 1 ohm. Then if you write the next KVL, V2 equal to 3I2. Yes or no? V2 equal to 3I2. This KVL, V2 equal to 3I2. So Z22 is 3 ohms. Because ratio of V2 by I2. So finally the Z parameters are, finally this is answer. This is minus 2, minus 8, minus 2, minus 8. And this is 3 and this is 1 ohms. That is the meaning. That is the meaning. In negative impedance is active regenerative model, sir. Why it is active regenerative? Why it is active regenerative? Because there is a dependent source here. There is a dependent source here. Okay, these introductions are a lot of things to do. Don't worry, I will go with there. Okay. So now, doubts you can ask. Anyone doubts? Anyone doubts? Yeah, Bhimilan is fine. Tell me your doubt.
Sir, already Sir, hello.
Tell me.
Sir, already you have told a point that a reciprocating is equals to passivity.
Yes.
And what does it mean? After that point
All
also.
passive. No. That means all passive networks are default reciprocal.
Oh, by default.
By default. That is the meaning.
And vice versa.
Okay.
Okay.
Right. Yogesh, what is your doubt?
Yes, sir. Sir, we have solved that Laplace transform using problems, no, sir.
Tell me.
Sir, in that, how to find the damping, sir? Whether it is critical damped.
You see the transfer function. You see the transfer. That is why transfer function analysis will start. I will tell you such things. See, transfer function, I will show you. For example, coming from here, let us say gate problem. See, now if you look at this transfer function, now you see here clearly the poles are negative
-1.
-1 negative. And also if you find the roots here, you will get definitely complex conjugate here for this.
Yes.
So that is why it is like in your control system, zeta 0 to 1 means underdamped.
Yes.
And in the second case you see roots are negative real equal means critically damped.
Yes, sir. Yes.
Like that you can tell. Okay na? Control system, like it almost enters control system now. That is why after networks we almost enter control system now. Okay.
Okay, sir. Thank you, sir.
Okay. 1 minute, everybody. Everybody, good news. Yes, everybody, please raise your hand. Those who are there, please raise your hand. See, everybody listen now. Put down your hand. Everybody put down your hand. See, tomorrow 7 to 9:30 close, sir. Syllabus will be pakka close. Okay, na? 100%. So it is confirmed that tomorrow 7 to 9:30. But 10 onwards digital. 10 to 1 digital. Everyone note down this, please. Everybody note down this. See, tomorrow 7 to 9:30 again networks. We are closing everything, sir. Pakka 100% we are closing. Then I will share my notes on everything. Okay, everything I will share, and doubt session also I will put. In doubt session, extra topics, etc. I will teach if necessary. Okay, na? So tomorrow, everybody remember 7 to 9:30 networks, 10 to 1 will be digital. Okay, na? Chalo, no doubts. Beamline is fine. Any doubt? Any more doubt?
Yes, sir. That transient we are calculating in the power system. Power system we are calculating.
Doubling effect, critical clearing angle, such concepts will come there.
Zero current arc interruption method.
Zero current is impossible, but if you can open the circuit breaker exactly at that point where current is zero, then no transient will come, because transient during turn off will come because of initial condition only, na?
Okay. Sir, here also you have done a point that we have the DC offset will be maximum.
DC offset means the doubling effect concept, that also is related to doubling effects concept.
But here sir, you are directly taking that sine term will be some -1.
Because here positive maximum. I asked a positive maximum. See here, positive maximum.
But exactly t बराबर 0 means t बराबर t naught e to the power minus t naught by tau is some value.
It will be, but maximum will come when this value, see, that is an however exponential decay function. This is however exponential decay.
But we are not
DC offset is a starting point that will shift the overall voltage. Na? See, at t equal to 0, this e power 0 is 1. Na?
Yes, sir.
That means maximum will come when this is automatically 1.
Okay, but sir, at in a gate problem, it is given at t बराबर t naught.
No. While opening it is T naught, but DC offset value at t equal to 0, we plot from there.
Okay.
Okay.
We are not going through derivative method, sorry.
No. The same also will come. You can take that di by dt equal to 0 also. Same concept will come.
Means that Vm by z sin theta minus phi is a constant term.
Same concept.
And e to the power, but it will be complicated more.
Yes, same will come. Okay. Okay, right. So tomorrow everybody listen. 7 to 9:30 networks close and 10 to 1 digital. Okay.